της Σχολής ΙΜΗ του Πολυτεχνείου Κρήτης. Θα είμαστε για 3 ημέρες εδώ με νέα μέλη, πρώην μέλη του Πολυτεχνείου. Νομίζω θα έχουμε πολύ ενδιαφέρουσες ομιλίες. Ευχαριστώ όλους τους φοιτητές ή τους ενδιαφερόμενους οι οποίοι συνδέθηκαν, πιο πολύ τους ομιλητές. Και την Παρασκευή το απόγευμα θα κλείσουμε μετά με ένα session για ανοιχτά προβλήματα. Έτσι, οι ομιλίες θα είναι στα αγγλικά, οι ερωτήσεις θα είναι στο τέλος, άρα αν θέλετε σημειώστε τις ερωτήσεις προς το τέλος. Νομίζω οι ομιλίες είναι περίπου 1 ώρα και στο τέλος έχουμε ένα τεαρτάκι και να περάσουμε από μια ομιλία στην άλλη. Μπορεί να έχουμε κάποιες ερωτήσεις. Έτσι. Οπότε, Παναγιώτη, σε παρακαλώ, αρχίζεις.
Sure.
Σε ακούμε.
All right. So, thank you very much, Professor Lavas, for your kind introduction. It's a great pleasure for me to be here for the second time in this summer school series at the Technical University of Crete. The topic of my talk is improving convolutional neural networks towards real-time multimodal object detection in remote sensing imagery. Few things first about my connection with the Technical University of Crete. I'm an alumnus of the ECE department. I was in Chania between 2004 and 2011, and I received my engineering diploma degree and master's degree in ECE. My master's advisor was Professor George Karistinos, and we did some very exciting work on reduced complexity optimal receivers for space-time coding. And every time that I go back and think of the work we did in the Technical University of Crete, I'm always grateful for the foundations that I got and for the experience and the things that I learned while I studied at the Technical University of Crete. And it's always with great pleasure that I come back to give this talk, or sometimes in person when situations permit. Currently, I'm an assistant professor of electrical engineering at the Rochester Institute of Technology, where I direct the machine learning optimization and signal processing laboratory, which has the acronym MILOS, like the Greek island. And currently, there are 6 PhD students in my research group, and our research is sponsored by the National Science Foundation, the Air Force Office of Scientific Research, and the National Geospatial Intelligence Agency of the United States. Our research focus is more so on optimization for signal processing and machine learning, but also currently we're looking into algorithms for tensor analysis, algorithms and theory. And also, more recently, we're looking into neural networks and how we can improve them theoretically, but also practically for new challenging applications. And this last one is the topic of today's presentation. Just to give you an idea of those of you who don't know where Rochester is. So Rochester is in New York State. It's what we call upstate New York or Western New York, depending on who you ask. It is on the south shore of Ontario Lake. And you can see a picture in the middle of the skyline of Rochester. And on the right, you can see the campus of RIT. And here I have a picture from last spring, or yes, right after the Christmas, with some of my students. You can see here Dimitris also, who is attending this seminar. And today I will talk to you about the first findings that we had in a new research direction that we started very recently. And this direction is target tracking in multimodal aerial imagery. So we have already some exciting findings, and I thought that it would be timely to share these findings with you today. The scope of this research is to design learning systems that can detect and track targets in streams of multimodal aerial imagery. And we have a 5-year project from the US government for this research. The results that I will present today were found together with my collaborators, Dr. Eli Saber, Dr. Ray Patucha, and our students, Manish Sharma, Mayur Dhanaraj, Dimitris Kaklakis, Yilong Yang, and Sri Karnam. Just an outline of my presentation. I will start with some background and some motivation, and then I will introduce one by one the proposed solutions on how to improve convolutional neural networks for the problems of interest. And then I will present some experimental studies that illustrate the performance of our methods. and then I will summarize with some concluding remarks and some references for our future research. So as I said earlier, the problem of interest here is object detection. We call it detection, but really we mean both localization and classification of objects in images. So not only we want to find where they are, but also what kind of object it is from a collection of classes, of possible classes. So in the figure on the right, you can see, for example, that we have a highway and we see a picture of a truck. There are multiple cars, there is a truck, and we're able to identify where is the truck and identify that this is a truck and not a car. So we care a lot about both finding them and telling which class they belong to. Some of the applications of object detection include autonomous navigation, and you can see in figure 4 some examples, robotic autonomy, defense and security, search and rescue operations, and many others really. It is what we call in computer vision, object detection is omnipresent in computer vision applications. And then there are basically two categories of methodologies for object detection and classification. Broadly, we would say that the first category are the non-deep learning approaches or traditional approaches, and the second one is are the deep learning based approaches. So in the non-deep learning approaches, typically we have handcrafted features, so features that are selected by someone that knows the properties of the data, and then tries to identify features that could be helpful for the problem at hand. So features that could be helpful for identifying targets, for localizing targets, and for classifying targets. And then in deep learning, typically what happens is that we have a neural network that does joint feature extraction and detection of targets. So when we say deep learning approaches, typically we refer to convolutional neural networks. There are some benefits to such approaches. You know that they're increasingly popular over the last few years. Some approaches are that they're end-to-end trainable. Other approaches are that you let the data determine the features that you care about. Of course, there are also some considerations with regards to their computational efficiency, how hard it is to train them, how much data you need, how much time you need, and what are the resources. But performance-wise, one could say that when the resources are available, deep learning approaches are currently preferred in practice. Now, in this specific project, we focus in approaches that are real-time. So we want to design efficient networks that can very quickly learn, and we can deploy them with a small collection of data and train them easily. So here is an overview of some of the state-of-the-art approaches for convolutional neural networks for the problem of object detection. So the first one on the top is what we call RCNN, stands for regional CNN. And then we're using a convolutional neural network to predict bounding boxes within candidate regions. And this procedure is computationally intensive. It was one of the first approaches that predicted bounding boxes within regions. It was quite successful performance-wise, but computationally intensive. Therefore, this motivated researchers to look into more computationally efficient approaches, and this gave rise to a line of research, starting with fast RCNN, so fast regional CNN, or basically the region of interest. There is a region of interest pooling layer on image feature maps. There is an optimization of the prediction for the bounding box that makes it computationally faster. And overall, this computational benefit comes at minimal performance cost. And then we have the faster RCNN, which you have a CNN now to choose the candidate region. It has even reduced computational complexity, and it's end-to-end trainable. Overall, we would say this would be one of the fastest, the faster of the RCNN in the RCNN line of research. And then we have a new line of research that started in 2018 with the YOLO V3. This YOLO means you only look once. And this is the most recent version is the third version that starts from YOLO and then YOLO V2 and now V3. This is real-time trainable, and it has also high performance in detecting and classifying targets. Now, YOLO v3 has found very broad application over the past couple of years in computer vision problems. So for example, in autonomous vehicle navigation, YOLO v3 has demonstrated very good performance with low training cost. However, these approaches have not been tried or have not been optimized for application on remote sensing imagery. So, and as I will talk about later on, there are many differences between computer vision applications and remote sensing applications that pertain to the nature of the data, but also to the tasks. So I'll talk more about that later on. So just to give you a quick overview of the YOLO architecture. So it is a fully convolutional neural network. It has 75 convolutional layers, 31 other layers that include shortcut, route layers, some sample layers, etc. Overall, we can say that this has 106 layers. As you can see right here, there are 3 detection heads for 3 different scales of objects. So when we say scales of objects, I mean really sizes of objects. So within an image, you can specify 3 different scales or broadly sizes of objects that you can be looking for in this particular architecture. So small scale, medium scale, and large scale. Also, for each of these detection heads, there are multiple anchors, specifically 3 anchors per detection head. And when we say anchor, we mean really, we refer really to the orientation of the bounding box that we're looking for. So, for example, in scale 3 that we're looking for larger objects, we can be looking for objects that are square or for objects that are rectangular in a wide sense, wide rectangular or tall rectangular, right? So this is just one example of 3 different anchors that you can have per detection head. As I said, the detection performance is quite good, and more importantly, it's computationally fast to train. Now, what the output of this neural network is what we call a prediction vector, and this prediction vector returns coordinates for the bounding box that includes the target, and you can see those coordinates. So on the top of this vector, you see XC and YC. These are the central coordinates of the bounding box that includes the target. W is the width of the bounding box, and H is the height of the bounding box. And then P is the objectness. So it's just a variable that takes higher values if there is a high probability, let's say, that there is a target in this bounding box. And then we have a number for its class. And by these numbers from 0 to 1, which says which class is more probable for this particular object. So PC1, for example, if PC1 is close to 1, this means that probably this object is from class 1. So this is just a quick overview of the YOLO v3. The reason that I present that is because we will see how we can optimize this network specifically for remote sensing tasks. So a few things about remote sensing. And when we say remote sensing, typically we mean data that are collected from aerial imagery, for example, or synthetic aperture radar, right? So some sensors for remote sensing that we will be considering in this project are RGB, light, from above. So we care about aerial imagery. And it is within the interest of this project to learn how to combine the data from diverse remote sensing modalities. So we have, now in this particular remote sensing applications, there are some particularities to which we want to take into consideration. For example, the targets, in contrast to computer vision applications, the targets here are typically very small. So they will occupy just a very small number of pixels within the image, meaning that we're looking for, it is much harder to find a target, but also it gives us a very few very small margin to identify features so that we can classify it. And this is in contrast, for example, to computer vision applications. Think of an autonomous driving vehicle for which an object actually could be a car, could be a bicycle, could be a pedestrian, and this occupies many pixels in the scene, in the frame, in the video frame that, for example, that the car is recording. So this is one specification of these applications that makes them quite different than computer vision. The other, another challenge is that we have, in many cases, we have noise, occlusions, compression, artifacts. Now, depending also on the modality, we may have thermal interference, etc. And then another concern is that the targets are typically not, they don't have the same orientation. So for example, if you're looking for a car, the car is, you may find the car to be rotated in any possible way, while in computer vision, you wouldn't find, typically you wouldn't find the car upside down. In the case of remote sensing, you may find cars rotated in any possible way. So these are some of the challenges that make object detection in remote sensing significantly different than object detection in computer vision. And we will do several modifications to existing neural networks in order to accommodate and account for these challenges and manage to give a better performance than state of the art. So the first direction that we looked into was fusing multiple modalities. So we said maybe we can combine RGB and infrared, and we can fuse these modalities in a way so that we can get the different information from these two and combine it in a way that can give us better target detection. So in this example and in this talk today, I will be presenting data for fusing that we get by fusing RGB and IR. So red, green, blue, 3 specific channels of the color, and then IR, infrared. And the idea is now, how can we fuse them? Now, typically, what people have been doing is they have been fusing diverse modalities at the entry point of a neural network. So the what they call early fusion. Now we will see how we can modify that and make something possibly better than this. Another point that I want to mention here is that there are many challenges when you have to fuse image data that you have to consider. For example, you would like this data to be co-registered. So you would like this data to, you would like same pixels to correspond to the same area in the scene that you are recording, or to know in what way one picture is a transformation of another picture. So we need to have some kind of pre-processing that co-registers images from different modalities. And I will be assuming for the rest of this talk that we do have this pre-processing mechanism, and that all our data are, as we call, co-register. Okay, so I'm starting with a data set that we call the, which is called the VEDI data set, vehicle detection in aerial imagery. So this data set contains, for example, contains RGB and IR in two different sizes. So 1024 by 1024 and 512 by 512. There are many different backgrounds in this data set, and there are 2 modalities, RGB and infrared, and we have 11 classes of vehicles. So now talking about fusion, and assuming that we have at least 2 modalities of co-registered data, the question is how we can fuse them. And as I said, people have been doing early fusion. There are a couple of works that do that, early fusion, so fusion of the data before you give them in the network. And typically they do that by concatenation. So you see we have these 2 main questions here, how to fuse and where to fuse. When it comes to where to fuse, people have been answering early fusion, so before you give them in the network, before you give the data in the network. And then an alternative approach that we have considered in this project is to do mid-level fusion. So we can possibly fuse data at any different point within the network before decisions start to be made. Another question is how to fuse. As I said, one way to fuse is by concatenation. So you can consider IR to be a fourth channel. So you can have RGB, IR, 4 channels given at the input of the neural network. Other approaches, of course, are possible. All kinds of ways we can consider and test for fusing the data. In this specific presentation, I will be talking, apart from concatenation, you will see me presenting results on element-wise cross-product between feature maps. So let me show you what this means. So you see here in figure 10, we have 2 modalities, modality 1 and modality 2, and each one of them is processed individually by a part of the convolutional neural network. For example, the YOLO V3 that we saw earlier. And at some point, we can stop this neural network. We have 2 streams. We can stop them at some point, at some level. And at any level, what we have is some feature maps. So a collection of weights, let's say, from the neural network. And at this point, we can decide to fuse these. And one approach to fuse them is to concatenate them. So we concatenate the 2 feature maps into a larger one. And another approach that I'm showing here is the element-wise cross-product. So you see how A and B look like tensors, and you can consider the frontal slabs of them. So what we do is a cross-product between all the frontal slabs of these 2 tensors, and this product is element-wise. So one slab with another slab get an element-wise product. So this is just another approach that we have studied so far, and it demonstrates actually sometimes better performance than concatenation. However, it results in a much larger feature map after the fusion. And there are many other approaches. Now we're considering, we're applying tensor methods in more recent results. But at this point, what I have to present is concatenation and element-wise product. So we apply the proposed mid-level fusion in the YOLO V3 network that I presented earlier. And we see how we can have the 2 modalities, and we have 2 streams of the network. And then at any specific layer, for example, the nth layer, we choose to do fusion by concatenation or by element-wise product. And that will result in a single feature map, which then we can continue with it as input to the remaining of the network stream. And at the end of the day, we will have again 3 scales and detection at 3 scales with multiple anchors, etc. So apparently this architecture can easily extend to more than 2 modalities. We can optimize, or we can choose in an informed way at which layer to do the fusion, for example, by cross-validation. And also we can optimize, as I said, the method of fusion. For now, we'll be talking about concatenation and element-wise product. So the modified YOLO V3 looks something like that. So you see now we have 2 streams. One is the RGB and the other is the IR, and we did the fusion at layer 38. And then we continue with the rest of the excuse me, with the rest of the network in a similar structure as it previously had. Of course, we have to introduce some layers to upsample or downsample accordingly, based on, in order to prepare for the concatenation. So you know that the output of layer 38 is supposed to have a particular size as expected by the next layer. Therefore, we may want to downsample the input of the fusion, or to accordingly downsample the output of the fusion, so that the sizes are conformable for the rest of the neural network. Now, so one approach for us is to do a fusion. Another approach that we can follow to improve the performance of the neural networks for remote sensing applications is to do data augmentation. So there are 2 main categories of data augmentation that we have been considering. One is geometric, which means that we take the image and we flip it, we rotate it, and then we do something else, which we call jumble up, which basically means that we crop different parts of the image and we rearrange them so that this looks like a new image, but really it contains the same targets, just at a different location within the with a bigger image, and probably with possibly with a different rotation also. And then other approaches are photometric approaches, where you can change the contrast of the image or the brightness, etc., and consider it to be a new data point to be used for training. Okay, now a few things that I want to say about other improvements that we can do. So remember, as I said, we're looking for bounding boxes in the image to detect objects. As you can see, in the output of the YOLO v3, we may have many bounding boxes around. Some of them actually capture objects, some others do not capture objects. And we have to have a decision on how to actually identify which bounding boxes actually contain objects. So remember, this output vector had this objectness variable, based on which we actually keep only few of the bounding boxes. And then actually we can identify which is the bounding box, which are the bounding boxes of interest. And then among those bounding boxes of interest that go around the target, we can choose the bounding box that exhibits the highest IOU. The IOU stands for intersection over union. So you see that if we have multiple bounding boxes on that car on the left, we can choose the bounding box that captures most of the object, and this is measured by this intersection over union metric. All right, so here is an example of the intersection over union. So you see, for example, this car on the right, and this blue is the predicted. This blue is the ground truth of the object, and this red is the predicted area. The intersection over union takes the intersection of these two areas, which is the green shaded area, and calculates the ratio of this area over the union of the two, which is the union of the blue and the red. And this way we can set a threshold and say that if the value of the intersection over union is above a specific threshold, then we did a good job in finding that object, right? Because as you train the network, you need to give a feedback to the network to know whether the object was found or not found. And in this case, the answer is given by the intersection over union. So if the intersection of the union is above a threshold, we said that indeed we found the object. And there are two parts here in measuring the loss of the network. One is whether you found the object or not, and then another part is whether you managed to find the class of the object. And these two parts, these two things participate in the loss function of the network. I'm just presenting here the intersection over union because we will see that this will be modified in an interesting way when we want to account for when we do other modifications to account for remote sensing imagery. All right, so here I would like to show some results on how YOLO v3 works with Fusion, and I will demonstrate some results on the VEDA dataset that I presented earlier. We consider about 1,200 images with resolution 512 by 512. We have two modalities, RGB and IR, and we study only 8 out of the 11 classes, the ones that are most commonly, the ones that appear most commonly in the data. So car, pickup, camping car, truck, other, it's a class, tractor, boat, and van. And then we have some parameters that we have just included in the slides. For example, what is the mini batch size for the training of the neural network? How do we initialize? What is the initial learning rate? The weight decay parameter. We also do data augmentation by flipping, vertical and horizontal. And the results are presented on a 10-fold cross-validation. So we're using 10% of the data for training, 10% for testing, and then we do 10 different such selections, partitions of training and testing data. And we try Fusion at 3 different layers. Actually, we did exhaustive studies for Fusion over all the layers, but here I will present just 3 layers, 6, 20, and 38. And we consider Fusion with concatenation and element-wise product. The metric that I will be showing is the mean average precision, and it is defined as shown in this equation. So it is the summation of, it is the average of the average precision that you get for each class. So we have 8 classes, the mean of the average precision, and precision, this average precision is the area under the precision recall curve. And then precision, we know it's the true positives over the total number of positive decisions. And recall is the number of true positives over the total number of positive in-ground truth. So we get the precision recall curves, we measure the area under the curve, and this is the average precision for its class. The average of that across the classes is the mean average precision. Okay, so first we want to identify the importance of the thresholds. Remember, we had three particular thresholds. One was the objectness, the other was the non-maximum separation, and the other was the IOU threshold. These three thresholds affect the performance of the network. And we exhaustively tried combinations between these three thresholds, and we identified, and we're plotting here the map versus combinations of these values. And we have a curve for YOLO with only YOLO v3 only with RGB, YOLO v3 with IR, and then YOLO v3 with early fusion of IR and RGB. And this early fusion means fusion at the input by concatenation. And then we have YOLO v3 with mid fusion at layer 6, and mid fusion at layer 6 with element-wise and element-wise product and element-wise product, giving emphasis to the IR or to the RGB. There is a way, we have used a way to give emphasis to different modalities in that fusion. I have skipped that in order to keep the presentation shorter. But what I'm saying here is that we have tested giving more emphasis to one modality and more emphasis to another modality in this element-wise product. And then we have YOLO v3 with mid fusion at layer 20 and 38 with concatenation, and then 38 with element-wise product, etc. In all of these studies that we did, and again, as I said, we tried almost all of the possible combinations here, but I just present few. We observe that the best performance or the highest performance is attained for the lowest among the confidence thresholds, and the highest among the NMS thresholds, and for the IOU, specifically, for example, for IOU 0.3 gives a good performance. But importantly, you see that among all these curves, the highest peak is given by the YOLO v3 with mid fusion at layer 6. Now, it may appear that in MAP, the difference is very small. This is because of how the metric is defined. And you will find papers in the literature defining this metric in a slightly modified way. However, it makes a difference. For example, even that very small change in the MAP may actually correspond to a significant difference in detection performance. All right, next we're plotting the MAP versus the epoch index. Epoch index is the training epoch index, and we said that its network is trained for 200 epochs. And I have fixed the values of the thresholds to the values that we identified that work well. For example, the IOU was set to 0.2, the NMS to 0.1, and the confidence threshold was set to 0.7. And we keep these same values for all the experience henceforth. And what I'm plotting is the map performance versus the epoch index. And you will see that we're plotting standard YOLO v3 with RGB. So this YOLO v3 is the computer vision YOLO v3 without any modification, basically. And then standard YOLO v3 on IR imagery, on the IR modality. And then we have YOLO v3 with early fusion and YOLO v3 with mid fusion at layer 6. And we see that early fusion and mid fusion both outperform the unimodal approaches, with the mid fusion performing slightly better, especially for intermediate values of the epoch index. So we see that definitely there is a merit in fusing, and there is a promise in fusing at the mid layer rather than at an early stage. Some numbers here. We also compare with other popular, quite successful networks for object detection, such as the simple sort and shallow network, SSS-DET. and we also compare with faster RCNN. And we see that, for example, the SSS det, it appears to have slightly better map performance than the YOLO v3 at the mid-level with a mid-level fusion. However, this is the result as reported in their paper, and they were just talking about a single split. So it's just one realization. So it's not really apples to apples, this comparison, but it shows, but this SSS det was the state of the art at that point, and therefore we see that we managed to bring YOLO v3 with the fusion up to very close to the state of the art. And the faster RCNN, you see it exhibits a much lower performance. Overall, I would like to say that we have a 6.5% improvement by the fusion compared to just YOLO v3 on a single modality. All right, and here we have just some images on which we have annotated the results. We have annotated the bounding boxes, and we can see that, well, this needs some zoom in, but by doing a comparison, we can see how, for example, performance on this side is where the fusion takes place, sometimes is better than the performance without the fusion. This is just one illustration, but overall, consistently, we saw that fusion gives better detection results. Okay, so this was one modification that we did. The fusion was one contribution that we did so far. The other contribution was to actually modify the network itself. So instead of relying on the YOLO v3, which is a network that was optimized for computer vision applications, we tried to modify it in a way that makes sense for remote sensing data. So the first thing that we do is to consider that objects in remote sensing imagery tend to be very small. And therefore, we need to increase the size of the detection heads. So we need to look into smaller regions for targets than before. The other challenge was, as I said, that objects tend to be non-uniformly oriented. And therefore, we thought to modify YOLO v3 so that it can actually separately identify the rotation of the object. So you will see in this figure 19 how we go from the prediction vector that I showed earlier on the left to the new prediction vector. And we have one more variable here, which is that theta that actually captures rotation. And the benefit here is dual. On the one hand, capturing rotation helps us better rotate the bounding box, and therefore the bounding box ends up being tighter on the object. That's one thing. And the other benefit here is that by introducing that rotation variable, actually we disassociate the rest of the variables from the rotation. So the rest of the variables, for example, the classification, the objectness and the classification become rotation invariant because the theta has actually captured what matters for the rotation. So by decoupling object rotation with the other features, we get a dual benefit. And let's see exactly where in the YOLO v3 we do these modifications. One change is at the detection heads. As we said, we increase the size, we double the size of the detection heads. Then we introduce oriented bounding boxes, and therefore we need that theta to capture that orientation. We reduce the number of anchor boxes from 3 to 1. So remember what I said, that for every scale, we have 3 anchor boxes. One is for square objects, the other is for rectangular wide, and the other is for rectangular tall. When we introduce that theta angle that captures rotation, then you do not need anymore 3 different anchor boxes. You can just do with one anchor box that you can rotate in any way, in any possible way. And that actually makes training much faster. And then we do some other modifications, which I'm not saying here in detail just for the sake of time. But really what we do is this. This focal loss, instead of binary cross entropy, means that in the loss of the network, which is a function, so there is a loss function that takes into account how well we found the location of an object and how well we found the size of a bounding box and the orientation of a bounding box, and also whether we did a good job on classifying the object or not. So there is a loss function for that. And we give more emphasis in this loss function to errors of no objectness. So to put it simply, if the network finds an object where there is no object, then it gets penalized more than it was in YOLO v3. The reason is that in these big images where the targets are very small, you tend to have lots of background. So you don't want your network to actually return lots of bounding boxes and think that it has found lots of objects. Therefore, we give extra penalty for such mistakes of let's say false alarms. And then we did the necessary modifications to these connections here, the downsampling, etc., to accommodate for the changes in the sizes of the detection heads. So the three main contributions here were the change of the size in the detection heads, the introduction of the angle with rotated bounding boxes. We don't need anymore the number of anchors that we had previously, and we changed the loss function. These are the main modifications that we did, together with data augmentation, as I presented that earlier. So here you see the value of increasing the size of the detection head. So this is 16 by 16 compared to a 4 by 4. And you see that when you actually have objects of such small scale, it is more meaningful to look into smaller regions. Now, in order to look into smaller regions, you need to increase the detection head. Now, of course, we understand that this naturally would result in a higher computational effort to search it into these regions, into more regions, right? So now we're searching in 16 squared regions instead of 4 squared, 16 regions. But at the same time, as I said, we reduce the number of anchor boxes per detection head. And with the other modifications we did, in fact, we end up having a faster training process than what we had with YOLO v3. All right, so all these modifications that I showed earlier to YOLO v3, we capture them in a new name, which we call it YOLO RS, which means YOLO tuned for remote sensing applications. So now I'm presenting YOLO RS with mid-fusion, and it's exactly as it was the YOLO v3 with mid-fusion, but now this includes also all the modifications that we did for the YOLO RS. Now I will show some numerical studies on YOLO RS. Again, we will be using the VEDI dataset, same as before. The parameters are set same as before, so the mini-batch size and the initialization and the learning rate and the weight decay parameter. This time I will be doing geometric with flipping, but also I will be doing geometric with rotation. So I will consider rotations 90 degrees, 180 degrees, and 270 degrees. The reason that we want to do this data augmentation with rotation is because we want our network to do a better job in identifying rotations correctly. And also we do the jumble up, which is what I showed earlier, is a new method that we proposed for rearranging parts of the image to create new training data. And then we do also photometric with brightness, contrast, gamma, and grayscale. We do tenfold cross-validation, 10% training, 10% testing, and we do fusion at layers 6, 20, 38 with concatenation and element-wise product. All the networks are trained to 200 epochs. Now, in this figure, we plot the map versus the epoch index for YOLO RS, so the YOLO v3 with all the modifications I talked about earlier, but unimodal application, so only on RGB. And specifically, what we tune here is the number of anchors, the number of anchors 1, the number of anchors 3. Gamma is a parameter that tunes the local, tunes the loss function, as I said, to give more emphasis in false alarms or not. So we have gamma when it doesn't give more emphasis, and gamma is equal to 0, and gamma is equal to 3 when we give more emphasis. So you will see here that the number of anchor boxes, whether you have 1 or 3, does not really make much difference. So you see that the red and the black, the red is for 1 and the black is for number 3 anchors, pretty much gives similar performance for the same value of gamma. Similarly, the 1 anchor and 3 anchors for the value of gamma is equal to 3, so the blue and the magenta, again, demonstrate similar performance, especially for higher epoch indices. So this study actually justifies or verifies our initial assumption that because you have the theta to account for the orientation of the anchor boxes, you don't really need to have 3 anchor boxes, the wide and the tall and the square, but just one of them, just one rectangular suffices. The other thing that we notice here is that actually gamma makes a big difference. So see that by tuning gamma from 0, which was the standard loss that YOLOv3 was using, to 3, which places significant penalty on false alarms, for this particular data, remote sensing applications where the targets are few and the background is plenty, actually it makes a big difference, increasing the map from 0.5 to 0.56. So two take-home messages from this figure is that number of anchors, you can get away with one of them, and with just one of them, and the other is that penalizing false alarms actually helps a lot the network in these applications. Then we have another study where we plot now, again, the map metric versus the epoch index for the same parameters. And what I'm showing here is YOLOv3 on RGB, YOLOv3 on RGB with some improvements. So we introduced the rotation and the larger detection head, but not everything. YOLO-RS, the proposed architecture, on RGB, and YOLO-RS on IR. And we observed that the YOLO-RS, the magenta and the red, significantly outperform YOLOv3 for YOLOv3 on RGB, so just the standard YOLOv3, which exhibits very poor performance at about 0.42. And then they even outperformed the modified YOLOv3 with just rotations and larger detection heads. And we see, for example, that the proposed YOLO-RS on RGB can attain a performance of about 0.56. Also, we compare it with the SSS DET, which, as I said, was one of the state-of-the-art approaches for this task. And we saw that we actually improve on that by 22%. So we improve on standard YOLOv3 by 34%, and we improve on SSS DET by 22% in the map metric. And then again, here we have some illustration of the results on the actual images. Again, this just give a visual illustration of what of how this works. And you can see, for example, in the third column, how on the top you have YOLOv3, and this is maybe a thing that I would like to zoom into. So you can see how YOLOv3 actually places a tall, reasonably it places a tall bounding box around the object. But you see that because the object is not entirely vertical, necessarily the bounding box captures also some background. So the bounding box is not so tight around the object. On the other hand, allowing for the rotation that we introduced in YOLO-RS, the bounding box can be much tighter and you can much better capture exactly the rotated target where it is. All right, so now we want to see what happens when we fuse data from more than one modalities, and the VEDI dataset allows for that. So we're plotting again the map performance versus the epoch index for YOLO-RS with fusion at the input. So this n equals to 0 means early fusion at the input with concatenation. YOLOv3 with early fusion, again, at the input with concatenation. YOLO-RS with fusion at the 6th layer with concatenation. And then YOLO-RS with fusion, again, at the 6th layer, but now with element-wise product. And we see that definitely YOLO-RS outperforms YOLOv3. So all the modifications we did for remote sensing data seem to work quite nicely. And in addition to that, you see that mid-level fusion, for example, the blue line may actually exhibit, the blue and the black line may actually outperform the early fusion for YOLO-RS. Again, the difference is not very high in terms of these numbers, but in this kind of applications, even small difference is important to have, and definitely shows some trend and some possible merits in the mid-level fusion. Now, comparing with alternatives, we see that we have a 34 and about 35% improvement on top of the performance of YOLOv3 with early fusion, which was proposed in recently in the literature. We have a small improvement, So by concatenation of the sixth layer, this is the result that I'm referring to is concatenation of the sixth layer. So the blue line. We have a 6% improvement over YOLO arrays just with RGB, 12% improvement over YOLO arrays with just IR, single modality, and about 30% improvement on top of SSS det using only RGB. Okay, to summarize, our contributions, the main focus of this research is to modify, to improve existing successful neural networks that were used for object detection in computer vision applications and modifying them in a way that would make them successful now in remote sensing applications. This is the first step in a 5-year project that we just started. And I might say that the results so far are very encouraging. More sophisticated modifications will follow in the next steps we have planned ahead, but we started simple. So to summarize, what we have is we propose the YOLO RS, YOLO for remote sensing, with fusion. So both the modifications in the YOLO itself and the fusion are new contributions in this line of research. And this is a network towards real-time object detection with the ability to leverage multimodal data, optimized for remote sensing applications in the way that we discussed. And we saw that on the VEDDAI dataset, which is a standard dataset for these applications, we can be almost 35% better than YOLO v3 with early fusion, and almost 30% better than SSS det on RGB data, which is considered, it was published in 2019, and since then it's considered the state-of-the-art approach for this task. This research that I presented today has resulted in 3 publications. So we have submitted 2 journal articles and 1 conference article. The 2 journal articles are now under review. These works were done with my students, Manish, Sharma, Mayur Dhanaraj, Sri Karnam, Dimitris Kaklakis, and then with collaborators, Rape Tucha and Eli Saber. Also in the second paper, it was written together with my student Yilong Liang, who now has graduated from RIT and he works for Apple. In the next steps of this research, we will look into transcending from bounding boxes to convex hull bounding boxes. So instead of having rectangular, to go towards general convex shapes of bounding boxes towards more tight detection of the targets. We want to see what modifications could be needed for modalities different than RGB and IR. So the next modality we will be looking into is hyperspectral. And it's not very easy to find ground truth labeled data to test on, but we're working into that with some collaborators also at RIT. Then we will look into other neural networks such as graph, convolutional neural networks. We will explore self-supervised methods for pre-training and parameter tuning. So instead of us tuning the thresholds and all other parameters, this could be chosen by the data. And then design a built-in pre-processing chain for data that are not co-registered. So in many cases, data may not be co-registered, these images from diverse modalities, and we want to see how we can make a chain in the beginning of the network that can actually account for that. And as I said, we will look into different fusion also methods, including tensor processing methods for fusion, the feature maps in the middle of the network. All right, and with that, I would like to conclude my presentation. And thank you all for your attention and take any questions you might have.
Thank you, Panayotis, for the presentation. Are there any questions from the audience? If somebody would like to ask the presenter, he may do now. Proceed. Okay, I don't.
Maybe from Tasos Kyrillidis here. Yes. Just a couple of questions. I assume the interest here is for moving vehicles. So using sensor or radar sensor data, you look into Doppler features that you can perhaps incorporate.
That's a very good point. We have not used yet. We have not really accounted for the motion aspect yet. So we're treating these as just images instead of video frame sequences, but definitely incorporating that temporal correlation aspect into the detection will be one of the things that we should consider.
Okay, that's something for future work.
Yes. Right.
Okay, thank you.
Thank you.
Another question? If nobody else would like to ask, I would like to pose some question to Panos.
Yes.
Panos, I have at first two questions. If you can go please to slide 22.
Yes.
Okay.
This one.
We saw a plot here where in the x-axis you show a threshold, a value, which is continuous, I think. And then
Yes.
the y-axis, you show the accuracy of your method.
Right.
Okay.
Exactly.
What is difficult for me to understand is that at some points I see some, let's say, strong discontinuities, which means if I increase a little bit the IOU or threshold, then I see a large increase of the accuracy.
Yes.
Is this easy to explain? Is this expected or is something strange?
Yes, for example, that's true, and this may also pertain to an extent to the way that this figure was crafted. So if we look, for example, at the biggest jump, which is right at the middle of the figure, so right here, you see that this jump signifies two transitions. One is for the IU threshold from 0.2 to 0.3, but also at the same time for the NMS threshold from 0.9, which is a very bad NMS threshold, to 0.1, which is a very good NMS threshold. And actually, this, even though it seems to be a small change, this is not a small change because the axis is not increasing here, you know. So you see how we go from 0.1, 0.3, 0.5, 0.7, 0.9, and then we go back to 0.1, but now for a different value of the IOU. So basically, the difference in the NMS threshold is large here, and this is why we see this jump.
Okay.
So as I said, it's a little bit tricky how this figure was crafted, and it can be confusing exactly because this is not a continuous increasing horizontal axis. So these seem to be neighboring values, but they're not. They're actually the two extreme values.
Okay. Now, I think if you can go to slide 33.
Yes. Yes.
So you plot the epochs and the accuracy. And I see some of the methods, let's say the blue dashed line, increases. Does this mean that the algorithm has not converged, or what could happen if, for example, you would run the algorithm for 300 epochs and so on?
Right, that's a very good point. We did that study, not included here, but we did let them run for more. Some methods keep increasing, but soon after they converge. So we stopped it at 200 because at that point, some methods were trained only up to 200. So for fairness in comparison, but indeed, soon after, even the blue one is going to converge and reach a plateau. Pretty much the magenta has already reached that plateau. The blue slightly increases more, and the red also has reached the plateau. So we wouldn't see significant difference if we continued for another 100 epochs.
Okay, any other questions?
Pano, on that slide, have you experimented at all with the learning rate, changing the learning rate? Either adaptively or?
The learning rate was kept fixed in the studies, but I know that we have experimented with different fixed values, and I think that these were the figures. So for all the methods, we use the same learning rate, and I think that the students had chosen the learning rate that actually gives the better performance.
Okay. Thanks.
Any other member of the audience? Questions to Panos? Okay, since we have some more minutes, I would like to ask my final question, Panos, which is probably the most difficult to ask. Okay. There is a chat message. Pano, can you please describe the VDA dataset? What is the input, the output, and the cost function of the neural network?
Yes. So I have another slide that I could show on the loss function. It's a little long because it has many terms, but I will try to describe it in words. So the input of the network is the images from the different modalities as we have it now, the images themselves. And then at every layer, operations take place on the images. We create the feature maps, etc.
The images are successive in time?
Not really, not necessarily. So this VDA dataset is not, it's not like a video stream. There are images from different places and different time instances. It's quite diverse when it comes to location and time. And then processing takes place, and at the output we see what we call the prediction vector, which, as you saw, it has basically one element per class. So in this case, 8 classes, so 8 entries. One entry for the objectness, so whether we did find an object in this bounding box or not. And then 4 entries for the location of the bounding box. So you have the center of the bounding box, the width, and the height. So we have 4 for the location and n plus 1 for the n classes. Now we have a cost function that compares these outputs with the ground truth. Now we will have many bounding boxes at the output. And because we will have many bounding boxes, some of them will be empty, some of them will be erroneous. We will have to choose few of them. And that was this was the IOU step that I showed on how we reduce the number of bounding boxes. So the loss is calculated on these reduced number of bounding boxes. Now, how do we calculate the loss? We just take the sum of the squared errors between the true value and the ground truth for the center of the bounding box. So you have the true center, one coordinate minus the detected center same coordinate, same for both coordinates of the center, and then squared error for the width, squared error for the height. And then we have some log functions that take into account whether there was an object there or not, and for the different classes that the probability to belong to each of these different classes. It would be, I know it would be clearer if I had here the loss function, but really it's a little tedious. And it's not really, we haven't really done anything sophisticated to it other than taking the squared errors. The only thing that we improved in that was to put more emphasis to false alarms, so that we can reduce significantly the number of false alarms, because we expect to have mostly background in the remote sensing imagery. I don't know if does this answer?
Yes, yes, thank you.
All right, thank you.
Any other question?
There was one in the chat.
Yes.
I think I can. Okay, so there was. Yes, would you like me to read it?
Mr. Fangias, can you hear us? You wrote a question in the chat. Could you explain the significance? Okay.
Can you hear me now? Yeah. I would like to ask, what is the significance of jumbling the image up? When you cut the image and rotate it and jumble it up?
That's a very good question. So what happens is that when you jumble up the image, then you will move the targets at a different location of the image, and also you will change the neighborhood. You will possibly change the neighborhood of the targets, because depending of course on how you crop the image before you how you cut it before you rearrange the pieces. Now, if you change the neighborhood of the targets, then when you take the new image and partition it into regions, each region will contain possibly the same target as before, but now with different with different neighborhoods. So it creates a new example, or almost a pseudo new example on the target, on the same target, but on a different background. And if this is combined also with rotation, then it can actually make the scene look significantly different. And this gives us, for free, an additional example to train our network on. Does this answer your question?
All right, thank you.
You're welcome. Thank you for the question.
Any other question? Okay, let me do the final again. Pano, I see that in your networks, you use, if I remember correct, 64 layers.
Right. So yes.
Okay, so this is a deep network, let's say.
It falls in the category of deep networks, yes.
Okay, and the data set, you have, if I remember correct, 1,246 images.
Right.
Of course, you do a lot of epochs. If I understand correctly, epoch means one use of every data set, every data point, let's say.
Yes, one new batch of measurements, yes.
Yes, I think I wouldn't call this data set a big data set, or no?
No, it's not a big data set, not at all. Not for this size, not for this size. Because there is one consideration on, big data set for the task at hand. This is definitely not a big data set for the task at hand. And that's why we need to do data augmentation to actually create more examples so that we can actually train the network. It is challenging to find data that can have both multiple modalities and co-registered and include ground truth in the form of bounding boxes. Some of them do include ground truth in the form of segments, which would be a kind of a different story for this network. And therefore, we found this one, which is quite standard and people have been using it, but it's not large enough. We needed to do substantial data augmentation to actually train our network with it.
I imagine that this network probably is not suitable for real-time tracking, or no?
The training happens, so they call it real-time network. The reason is that it can train quickly. Now, when we say quickly, for the data size, for the data set sizes we have, that meant a few hours. So to train the whole network within a few hours, 3-4 hours, is quite fast. I mean, it is considered to be. So the training takes few hours. Now the testing is actually fast. So it is actually real time, the testing, because it can, I don't remember now what is the frames per second, but it can actually do multiple frames per second. So it can actually demonstrate real time in the testing, right? Not in the training phase. In the testing phase, it can actually operate in real time with multiple frames per second.
Okay.
So you spend a few hours to train it, and then when you take it with you, because of the size it has and other aspects of it, it can actually attain a multiple frames per second speed.
So the training is, let's say, the beginning, and then you use it. For example, what happens if the testing data give you new information?
Right. That's a very good point. This is not accounted for, so we don't keep learning online as we test.
So I stop here. I would not like to monopolize discussion. Panos, thank you very much.
Thank you very much. It was a pleasure.
If there is any other question, please, now is the time. Otherwise, we will have a short break for 2-3 minutes until our next speaker, Tasos Kyrillidis, is ready to start. So,
yes. And if I may add, I have my email at the bottom of the slides. So, and also it's like my first name, panos@rit.edu. That's an alias email. So feel free to send me an email if you have any questions at a different time.
Thank you very much, Panos.
Thank you.
So we can stop. Okay, stop sharing. And Tasos, if you want, you can start sharing.
Good morning. How are you?
Fine, Tasos. It's evening here, afternoon, I would say. It's morning to you, for you.
So let me do that. I assume that you can. Awesome. And then if I do this, you actually see this. Awesome.
So just give a very small break, two or 3 minutes, and then Tasos will be with us. I think that the participants now, the number of participants has raised to 41. Zoom participants, okay? There is a live streaming, and I guess that many people are watching this on Facebook. So I guess, Tasos, you are ready, yeah?
More or less.
Okay.
But I'm okay waiting. It's up to you.
Okay. It's a great pleasure to present the second speaker, Tasos, as more common, Kyrillidis, which I have not seen for many years. He received both a diploma and his master's from our school. And then he got his PhD at EFL, if I'm not wrong. And after spending some time at Texas at Austin, now he is assistant professor at Rice University. Okay. Tasos, please.
Great pleasure, actually. It's been, Mr. Thanasis, it's been 10 years, I think. That's my first even virtual comeback to Technical University of Crete. So it's my great pleasure to describe and actually meet you guys. That's the important thing again. Today I will be talking about distributed learning of neural networks with a new technique that we have developed here at Rice. Given that it is a new technique, I would like this presentation to be more like also a discussion. So feel free to interrupt me if you don't understand something or if you want to clarify something. So I would like this to be more like a discussion. This is a joint work with Bin Hang Wan, a PhD student here at Rice CS, and Professor Chris Germain. Okay, so already Mr. Thanasis has done the introduction of myself, but let me do it also myself. I got my undergraduate at Technical University of Crete and also my master's. I have been working during my master's with Professor Karstinos. Then I did my PhD at the CS department at EPFL, where I worked with Volkan Sefher. And after that, yes, I started doing my postdocs at UT Austin for 2.5 years with several professors there, also 1 year at IBM in New York before I joined RISE at the CS department. So the general interest, and the reason I have this slide is just to advertise myself to students at the Technical University of Crete, which I really would love to have students here at in Houston. I'm working on optimization for machine learning and AI, algorithmic theory, and if you want to like put a label on it, like any problem that has an algorithm, and I would like to understand when and why actually it works. And I have a, let's say, a semi-annually, let's say, research keywords, among which is metric factorization, acceleration, implicit regularization, over-parameterization, and now I'm trying to get into more like quantum stuff. So it's like something that I'm starting to learn. So it's not that it's my expertise, and so on and so on. So if you feel like you like this, let's say, keywords or buzzwords, just let me know, and we can actually see what we can do. Okay, so I would like to start with a motivation just to give you an idea of what I'm going to talk about, and I'm going to describe the first scenario. So bear with me. So imagine that you have a big data set, you have your neural network, you have already implemented your algorithm, for example, on TensorFlow or PyTorch, and you have made your calculations because you don't have your GPUs here in your office, for example, and you would like to go for AWS, and you saw that it takes you 2 months to train this on a GPU, okay? And you cannot afford this time, actually. And you would like to say, you know what, if I pay double the price, I would like, let's say, to cut the training time to half. Okay, so that's the, let's say, the go-to scenario. This is what you would like to have. You would like to have an acceleration by the time you go from a centralized computation to a distributed computation. Okay, I would like also to stress out the second scenario, which is more related also to the wireless, let's say, community at the Technical University of Crete, where, for example, we have mobile machine learning applications, meaning that now the computational devices are actually mobile devices, which means that they're like, you have a heterogeneous network. Your devices are ephemeral in the sense that they can come in and out, and you don't know how they can help in the training of a global model. And you have also computational and energy, let's say, constraints, and of course, communication bottlenecks, as we all know from the courses by Mr. Lavas of wireless networks. Okay, so you would like to have, let's say, a distributed computation of whatever machine learning actually model on this kind of networks, which, for example, might have a lot of wireless devices, and you would like to have a stable, or not only stable, but at the same time efficient way to solve the problem. Okay, so this is more like a motivation. The general theme here is that, yes, we have data, we have a model, a neural network we want to train, but now I would like to have an efficient distributed protocol. Okay, so what is this talk about? It's about independent subnet training in neural networks, which I'm going to define. I'm going to define what is a subnet, but you can think of like a part of the neural network being trained on a different device. Each of these subnetworks are actually transmitted to the parameter server. I will define this also for reassembly. And the key attributes of this proposed framework are the following. We have fewer parameters sent over the distributed network. We have fewer parameters to be updated per device. And we can have longer local updates allowed. Okay. And this actually, even if it means like you have an approximation of the original problem, you get better final accuracies faster. So this is the fascinating thing. And this is what I would like to discuss it with you, even if you have an intuition or an idea on this topic. So that's the purpose of this talk, actually, not just to give you like, this is what I have done and this is a finalized project. Actually, the project that I'm actually describing has been recently funded by NSF and Intel. So this is the start of a journey, and I would like to share it with you guys, so in case you have any ideas. Okay. So again, I remind you, whenever you have a question, I don't know who is the moderator, please interrupt me, so I have no problem with that. Okay. So let me start with a background on distributed learning. And there are two main paradigms on how we do distributed learning. It's the data parallel and the model parallel. Let me start with the data parallel. Is the case where you have a bunch of devices or compute sites, okay? And in the most classical case, you have one of these devices to be the parameter server. This is where you keep all the most updated estimate of your model. And you have distributed the data into the other workers, let's say, okay? So each compute side, each worker, updates a complete copy of the neural network's parameters on different portions of the data, okay? So what's the classical algorithm to train neural networks? That's gradient descent based. It's stochastic gradient descent. So that's the full gradient descent, let's say, update, okay? And this is the picture where it describes what I said so far. You have a parameter node at the top, and you have all the workers at the bottom, where all the data on which you train your model are actually in worker 1 up to worker P. Okay, so what the data parallel does is the following. It says that currently I have a model estimate, which is XT. These are all the parameters of your neural network. Okay, what I'm going to do on this cycle, on this iteration, is that I'm going to distribute this information to each of the workers. Okay. Then the workers are going to actually compute their gradients, okay? And then at the very end, I'm waiting as a parameter server, I'm waiting all the updates to be sent to the parameter node, okay? In order to accumulate and aggregate all the gradients in a mini batch or a larger batch, okay? And do the gradient update, okay? That's the main idea, that you have to wait all the gradient paths. Now, if I want to characterize here some, let's say, if I want to describe some problems with this paradigm, is the following. First of all, you have to send the full model from the parameter server to each of the workers. Now, I have an example here that I say the following. Imagine that the input dimension, okay, this is your data input. Imagine that it is an image, which is actually, you stack up all the columns and you have a dimension of 100,000. This is a very logical assumption to make, okay? And imagine a very simple architecture of a neural network. This is just 2 hidden layers feed forward. Each one of them has 4,000 neurons, more or less, okay? This actually, and imagine that you have 64 devices, okay? And this is, again, a logical assumption to make, especially if you're talking about smartphones, for example, okay? Then you have also the batch size, meaning that how many, let's say, data samples you use per iteration. Bottom line, if you gather all this information together, it actually means that you have to send information from the parameter node to each of the device and back, because they send back the gradient updates. It is more than 100 gigabytes per round. By round here, I mean that just doing one iteration of gradient descent, or stochastic gradient descent in this case. So it means that this is not like a very reasonable assumption or a very reasonable realization of the system, because we're not going to send just for one iteration 100 gigabytes in order to train a model. Okay, so that's why data parallel, for example, is very efficient, and it's actually it's mostly used when you have big clusters. You have GPUs where they have very nice interconnections between the GPUs, and you have very fast communication. Okay, so that's the first one. The second one is the model parallel paradigm, where the idea here, let me go directly to the scheme, is that instead of sending the full model from a parameter server to each of the workers, you actually split the model to different, let's say, compute sites. Okay, so for example, the left one computer gets the green nodes, the second compute gets the blue nodes, and the, let's say, the rightmost node gets the green nodes. So somehow you split your X into parts. And what you actually do is you need a lot of synchronization, meaning that I'm going to do the evaluation from one compute node. So the forward pass is from computer 1 to computer 2, then from computer 2 to computer 3. Then if I want to do the back propagation, it actually means the same thing, which means that you need to synchronize a lot. And you know that in distributed learning, synchronization actually can kill any attempt that you make in order to accelerate things. Okay, so these are the two paradigms. Of course, this is a very high-level description. There are a lot of papers on this type of work where actually they try to pipeline this kind of operations as much as they can in order to minimize synchronization and do efficient things. Of course, I don't have the full list of systems plus ML papers, but this is the main ideas behind these two paradigms. Okay, any questions so far about these two distributed learning techniques? Okay, again, feel free to interrupt me if something is not clear from like, yes.
Also, I see a comment in the chat.
Sorry, I cannot see the comments right now. I'm in full screen.
Mr. Vitis, can you please ask the question?
Hi.
Hi.
With which platform do you parallelize the initial dataset to the workers? Do you use something like Spark or Fling or something like that?
That's out of scope, let's say, of what, like, this is something that I assume someone has done already. But yes, you can use any of these tools in order to do that. So it's not a restriction of the model, and it's not what we're going to discuss here. But yeah, I mean, there are different ways to do that. And we already assume that in the data parallel, already the data are distributed in the workers. And as I will describe actually later on in the talk, there is a notion of federated learning, which is where the workers already have data, and actually they don't want to share this data with other workers. It's a privacy issue. So how we split the data is not a restriction of the model, actually, of what I'm going to describe. Thank you.
Also, one more question. This is Dimitris. Yeah. So, yeah, I'm just wondering, so are you also going to talk about like all reduced type of aggregators where essentially it's kind of like sort of the parameter server setup, but unlike the case of the parameter server setup where the communication grows linearly with a number of workers, in like the ring reduce or tree reduce case, the communication is sort of constant with a number of workers?
I'm not going to get into that much detail, but yes, the idea is that I'm going to present a distributed model where it scales much better, almost linearly with the number of workers that you have. Of course, there are restrictions, and I'm going to explicitly state what are these restrictions. But I'm not going to get into this discussion of like or reduce and so on and so on. So no, I mean, but I'm more than willing to hear your opinion, your perspective on what I'm going to describe and what you know already about this these notions.
Cool, thank you.
Okay, good. So let me
ask you something?
Sure. Yes.
Sorry. On the second scenario, the model parallel, where are the data stored? Are they again distributed, or are they stored in a central node?
So usually it is in a central node, because as you can imagine here, is that in order to do the forward pass, you have to have the input. So someone takes care, and I'm not the expert here to describe every possible model parallel paradigm here, but you can imagine that one takes, like, you can store the data somewhere else. Like you can have another cluster, which is just another compute side, which is just the data collector that then feeds this pipeline, because you have to do the forward pass and then you have to do the backward pass. So it's not that all the nodes need to have access to data necessarily, but you can have different ideas here. You can have all of them connected to the data collector or the data center, or not. It depends.
Okay, thank you.
Okay, if there are no other questions, let me move forward. So what are the fundamental challenges here? Consider a cluster setting, meaning that you have several GPUs in a cluster, okay? And I'm going to describe some numbers here, like some of the now turn out to be classic examples of GPUs that you use in Amazon is the Tesla V100 GPUs, where we know that the memory bandwidth is very efficient, okay? But if you have to go between nodes that have GPUs, this is where the bottleneck is. Okay, I want to stress out here a small and a very small detail, there is this notion of NVIDIA link. So how you actually connect GPUs together if they are within one, let's say, tower, if it is within one box, compute box. Okay, this is much faster if you want to communicate between GPUs. But consider the case that you go beyond that. You have a lot of GPUs that go beyond the 4 or 8 GPUs that you have in one box, and you have to communicate with another compute node. So there you have to use the standard, let's say, Ethernet bandwidth, where now the communication is much slower. Okay. And of course, the notion here is to go beyond GPUs. If you have smartphones, there is no notion of very quick communication between devices. You have to go through the wireless channels. And again, you have a very low bandwidth when you communicate with a network. Okay, so there is a bottleneck here. And this is one of the bottlenecks that actually the parallel model has. The model parallel, like what are the limitations here? You might have limitations per device, for example, RAM. You might have limitations with respect to computational units. You have limitation with respect to synchronization. So definitely there are challenges. Okay, and the current trend is like neural networks are getting larger and larger. So this is so far what I said is just a motivation. We have some distributed paradigms that they actually work well in practice right now, but not exactly at the level that we want them to work. It's not that if you rent more GPUs on Amazon, that you will get actually the amount of acceleration that you need. Actually, it might be the case that it is the opposite. So we need to do some research and find ways in order to overcome these difficulties. Okay, and this is where the independent subnet training comes into play. And I try to explain the idea mostly through images. So they're going to be only little math. And I would like to hear your opinion about this. Okay, and I will start with very simple. This is actually a bottom-up description of a neural network, just for the sake of space here. Okay, so you have at the very bottom, you have your input, you have 1, 2, 3 hidden layers, and then you have your output. Okay, so this is a feed-forward neural network, and as you will see for the rest of the talk, this is where we're actually focusing on just for here. Okay, so this is, for example, what is the model that you actually have to share. In the case of the data parallel, you have to share all the parameters of the network. It means that you have to send all the numbers, the edges that connect, these are the weights that they connect from one layer to the other. Okay, and in many cases, these feed-forward layers take more than 50, even there are cases more than 70% of the number of parameters in classical, let's say, neural networks. This is where most of the computation and at the same time, most of the communication burden exists in just feed-forward neural networks. So what is independent subnet training? What I'm going to do is per layer, what I'm going to select without replacement a subset of the neurons. Okay, and I'm going to create this smaller neural network where I haven't subselected the input and the output. This is always selected, but I have subselected the neurons in the first, second, and third layer. Okay, as you can see, this is still a classifier, meaning that it is a weaker classifier compared to the left one. Okay, it just has a smaller number of weights that I have to worry about to communicate and update. And if I had this neural network from the very beginning, still I could classify, I could learn something, but maybe I don't have the expressivity power of the left-hand neural network. Let me create another neural network, which has as nodes something that does not overlap with the nodes that I have already selected. If you try and someone who is very careful see that every black dot on the middle neural network is not existing in the right-hand network. Okay, so for the moment, I just say I'm going to create 2 subnets where I have no overlap between the weights. Okay, so I will keep going just to complete the graph, and I have a third subnetwork, which again does not share any weights and neurons with the other 2 that I have actually selected so far. Okay, And the idea here is that the union of these parameters, of these weights, actually make the original neural network. So I have divided my neural network into 3 independent subnets, and I'm going to describe how I'm going to train my original neural network by training these subnets. Okay, is there any question so far?
Taso?
Yes.
This is Nikos. Do you replicate full connectivity this way?
Let me see, because that's the, there might be a case where you, let me see. You don't replicate full connectivity, and it's actually not necessary. It's like you might miss some of the weights, but what I described here is what happens in one iteration of the algorithm. So eventually you will visit all the weights, because the way that the algorithm operates per iteration is random. Next iteration, I'm going to do something completely different. So eventually I will visit all the weights, or I cannot guarantee that with certainty, but I will visit all the weights that I need of the original neural network. And as we will see in the experiments, this works really, really well.
Okay. Mm-hmm.
Also, one quick question. So so this is for full connected. If I want to use like convolutional neural networks, would it make sense to instead, instead of sampling activations, I sampled filters, just because it may make the implementation really easier?
Keep this question for the end, Dimitris.
Cool.
I will remind it to you, because it's actually an open question, and this is what we're working on right now.
Thanks.
Thank you. So I want to make one comment here, and maybe I can ask a question back to you guys. How does this relate to ensemble training in machine learning? But I haven't described what. Keep this question until I also describe what's the algorithm exactly. Okay, so given this decomposition, I haven't told you how I'm going to train this and how much I'm going to train these subnetworks. Okay, but the assumption that I make here is that I have 3, let's say, GPUs, and let's say 1 parameter server, and I'm decomposing the full network into each of the 3 workers as follows. So I'm going to go into this. Oh, I see movement in my slides, but what is shared in Zoom, it's not like with movement. But anyway, so I have made this decomposition, and I have the classical parameters server, let's say, setting. So what I'm going to do, and what happens in reality, is the following. First of all, the full network is actually kept in the parameter node, server node. Okay, what I'm actually sharing now over to the workers is actually the model only for the indices that they correspond to the subnets. So it's not that I send the full model to each of the worker. I only send the edges, the weights, that actually correspond to only the subnet that each of the worker is assigned to. Okay, so this is important, because now you, instead of sending the full model p times over the network, I just send at most the model once, because I distribute it and I split it over the workers. Okay, now what the workers do, okay, is actually each of the worker takes one of these subnets. Because each of these subnets is independent from the other workers, it's actually like training a neural network by itself, right? It's a weaker neural network, but it is strong enough in the sense that actually I can do local SGD updates. So in the classical data parallel, where you just send the full model, do the gradient updates, and you send it back, usually you actually don't do any more gradient updates locally. You actually, what you do is you compute the gradient, and the only thing that you have to do is to send it back to the parameter nodes in order to assemble all the gradients together and do the gradient step. Here, because each of the subnet is completely independent, I can actually do more than one local updates. I can keep improving my local neural network for, let's say, a number of local SGDs. I'm going, probably Dimitris has a question on this. Of course, there is local SGD in general, that it's not that you just do one iteration, but of course, this is definitely has nothing to do with asynchrony, and maybe each of the worker has a stale, let's say, a model, but in general, it is a independent subnetworks that I can actually do local SED with no fear. Okay, given that I have done some updates, I share the model back. Okay, which means that again, I don't share the full model, the full gradients or whatever updates I have to the parameter node, but only a subset of that. Okay, just I want to highlight here what are the good, let's say, so far perspectives and aspects of this approach is that I reduce the communication a lot. I don't send the full model to the workers and I don't send back full updates to the parameter server. And also each of the worker does not have to compute a full gradient because I have a subset of the neural network. I only have to compute smaller gradients in the sense that I have less number of parameters, which is very nice for them, for example, mobile devices, because they cannot just easily do backpropagation in a full network. If you can do backpropagation in a smaller network, that's awesome because it doesn't take too much energy and too much computation to do it. Okay, so this is just one iteration. This is what I said so far. So this is one iteration of the algorithm, which means that by the time the parameter node gets all the updates of whatever weights they were actually updated, now it gets into a new iteration, meaning I'm going to create completely different independent subnets in the sense that now these three subnets that you see are going to be different with the only, for the moment, with the only requirement that still they're going to be independent subnets. So updates from the previous iteration, like weights, they're going to be used with other weights because they're going to be mixed together. So different nodes different neurons are going to be mixed together. And this actually going back to Mr. Nico's question, more or less guarantees, does not guarantee, but more or less suggests that most of the weights are going to be visited at least one if you let it run for a sufficient number of iterations. Okay, so any questions so far? First of all, is this clear? Like, if it's not clear, I can repeat parts of it.
I have many questions. You were right.
Ooh, awesome.
It is really cool. So yeah, so the first one is at every worker is the so the network is trained according to the accuracy or the loss, the grain of the loss computed according to the smaller subnetwork, right?
Yeah.
So it's as if you optimize a smaller subnetwork. So I guess the question is, why do you expect that when you combine them, the accuracy of the overall network will be improved? So I think that's the thing that's striking to me.
Yeah, that's a question that we can discuss more. So yes, I want to stress out here that if I want to describe it with the ensemble training, so if you're familiar with ensemble training, the idea would be that you do the independent subnets once, and you train them until the end, and then you combine the classifiers. This is what the ensemble training is doing. And actually this boosts the accuracy because it is the notion of I have a lot of weak classifiers that if I combine them together, I get a stronger classifier. This is not what we're doing here because we just do for one iteration and I completely forget what the classifier was before because I reassign the nodes here and there and I have a completely different classifier. I will get to your question, Dimitris, when we get a little bit on the description, a little bit of math, but not like something that it's not going to be clear. But the general answer to your question is that we don't know yet why this happens. We have an intuition, but not in a math related, like we cannot state it in math why this happens exactly.
Taso, you are completely, so suppose you pick a subset of 100 weights for a particular worker.
Yeah.
Do you completely forget the previous values of the weights?
No. I combine them and I take the new values, whatever values I have, and this is what is shared in the next iteration. Maybe this was not maybe it was not very clear. So in iteration T, I'm at a specific state. So for every weight of the neural network, I have some weights updated from the previous iteration. I split the network into subnets, which means that I assign the weights that I currently have to create the subnets. Now I'm going to do SGD on whatever weights I have on each of the subnets. I get new weights. I serve them back to the parameter server, and I combine them some way. It's not that I forget the previous weight.
Okay, yeah. So you still have order of number of weights, communication, of course, per iteration.
Yes. So it is order one. So I send the model once per iteration, but I don't send the model P times per iteration, where P is the number of workers. Yeah, so if you imagine that I have 1 million parameters, in the case of data parallel, I send P times 1 million parameters, while in our case, I can send at most 1 million parameters per iteration.
Yeah, okay, got it.
Of course, this creates now, I'm talking in the general audience, the question, okay, it sounds like you're making a lot of approximations, and maybe eventually you're going to get less accuracy, but this is the surprising part, that actually you might even improve the accuracy. So let's describe a little bit about that, about this later on. So summarizing, first step, per iteration, we partition the model into independent subnetworks randomly, in the sense that it's not exactly randomly, because it is like without replacement. It's like I just make sure that there are no overlaps. I'm doing subnet local SED per worker on the subnets. And then after a number of SCDs, and maybe there is a synchronization that each of the worker does the same number of SCDs. Maybe there is a straggler kind of a situation here, but we can discuss it a little bit. I send my updates to the parameter server to combine them all together to the big network before I get again to the new iteration, where I split it again randomly, new neural networks, and I keep doing this like this as we go. Okay. So I'm going to go, and before I state a little bit of like, let's say some intuition that we have why this works, let me describe some terms here. Assume that we have n sites in a distributed system. By sites, I mean, let's say GPUs. I define as FL the activations at the ELF layer. So this is, let's say, the vector that comes out of the ELF layer. Again, we're talking about feed-forward neural networks. And what actually I describe can be described like mathematically, that you have membership masks. Per iteration, you create masks where they split each of the layers such that each of the subnet has a non-overlapping set of the neurons. So I randomly select for the first, let's say, worker, 1 over n, the probability to select one neuron, but of course I have without replacement. And I just make sure that from layer to layer, the way that I select the mask is actually completely independent. It's not like if I select neuron 1 in layer 1, I have to make a selection about the second layer. Okay. So the main idea here, and I'm not going to get into the details of that, is that if we do what we do from layer to layer, what you have as an estimator, like because you sub-select the neurons, is an unbiased estimator of what if you have done if you had the full network. So there is some math that actually proves that the way you select things, it turns out that the activations that you get into the subnetwork, okay, in expected values, looks like, or they behave like as if you had the full network layer. Okay, so this actually means that you can optimize the full network using the approximation of the network, because this is like on expectation it would perform quite well as you do that a couple of number of iterations. Okay, now do we have any questions about that? I know it's not like very well described here, but I would like to go a little bit faster in order to get to the results. Otherwise, it's meaningless if I don't present to you nice results. But again, the whole idea, maybe here it's a nice point to go back to questions that you guys had, why we think that this actually works. Okay, if you're familiar with the notion of dropout, what we do is actually a distributed version of the dropout, which actually means that per iteration, I'm going to create subnets. This is exactly what the dropout does. I'm not, just like as dropout, I'm not going to train it fully. I'm going to do one iteration, and then I just combine it together. Okay, so you can see this as a regularization term. regularization technique that actually, without creating weak classifiers as in an ensemble method, maybe locally it creates weak classifiers before you actually do the gathering to a full network. Okay, so if you see it like this, then, and if you believe in dropout, then this actually boosts the performance of a neural network. So what actually is needed on top of what I described so far, of course, is what you do during inference, or what do you do when you actually combine all the small networks in a full network? Because if you can think about this a little bit, imagine that you have a smaller network where the smaller network from layer to layer expects, one of them expects inputs at the level of 100, the other network expects inputs at the level of, I don't know, mean 0, and somehow you combine these things together in a big network. Of course, it's going to get the big network go nuts. Like some of the networks expect values at the order of 0, some of the neurons, they expect values at the order of 100. So you have to be careful here. And it turns out that batch normalization is the way to go. Actually, you just make sure for the subnets that every input to its layer is actually, let's say, whitened. It's like behaves similar to a Gaussian distribution, 0 mean and standard deviation. So what I'm trying to say here is it wasn't just like, okay, we split the networks and then we got them together and they just magically worked. We need to do some things on top of that in order to make sure that when we combine all the networks together, they are on the same, let's say, level of what kind of weights they expect from layer to layer to make it work. Because remember, at the very end, we are going to use the full network for inference. It's not that we train all these things not to compute, to use the full network at the very end. So we have to make sure that this is done smoothly and every network expects the same, let's say, level of in terms of weights. Okay, so
Taso,
yes.
How do you compute the mi and sigma during the process?
So you use the mini batches actually. So each of the let's say each of the subnetwork has local data, and you use the mini batch that you have per local for your local SED to compute the mean of the data and the variance of the data, and you just not exactly just, but actually you do a type of batch normalization. So it's not that was not the key thing of our idea, but there is a way to do it. It's not difficult. It's similar to batch normalization.
So you normalize the data, not the parameter.
You actually do this per layer. So you have to make sure that your input is actually whitened. Then this means that actually for the first layer, you're good. Then the output of the first layer, you can see the first layer as your input to the second layer. So you have to make sure that you use the mean and the variance of your data in order to make sure that all of the layers expect around the same level of weights. So it's just the idea of batch normalization.
Quick question. So yeah. maybe you're gonna talk about this in a little bit, but how do the individual subnetwork accuracies compare to the larger one?
Not as well. It's not that if you do ensemble training, it does not work, but the fact we tried, that was a very key question that we wanted to make sure that we're not doing something trivial. We saw that we have wide enough layers that they boost the performance, and at the same time the weak classifiers from like the subsets are not too strong to compete with the full network. So we have examples where you need the full network to get to the accuracy that you will actually expect, and you cannot do that with like weaker classifiers or ensemble training.
I guess maybe a simple way to ask my question. So if the full network has accuracy, whatever, 100% or like 99% on CIFAR10, right? Yeah. So what's the accuracy of the small, like of the subnetworks?
By itself?
Yeah.
We haven't, I don't remember exactly the values, but definitely it's lower than that. Like if you ask me in CFAR 10, I wouldn't test it. I didn't do that because we have some experiments on actually the full ImageNet with the 21,000 categories, which I don't believe that anyone has done this. So it's something that I cannot report right now. I don't have the numbers, but that's a good question.
Yeah, the only reason I'm mentioning this is this is kind of like an important problem for like federated learning. So we've been collaborating with some folks from Google, and they want to have like skinny networks at the edge, but train kind of combine them in a larger network at the service provider. And
really?
If your subnetworks had, let's say, very close accuracy to the full network, that would have been really really good.
Okay, good to know. So I would like to learn more about this actually. Okay. So just highlight, before we go to the experiments, highlighting the practical advantages. Again, subnetworks share no parameters between them, so there is no synchronization, and each of the worker can train for a larger number of iterations. Okay. It's a fully operational model, each subnetwork. So I can run it for a large number of iterations, and we know that also local SCD is something that boosts the performance in general of neural network training. The communication costs are actually reduced, and we have a smaller number of weights. And again, because of the local SCD, we also have less communication frequency. But instead of going here, let me skip also this and go directly to the experiment. So again, I remind you, I'm going to talk only about feed-forward neural networks. The CNNs that I have here, I'm going to explain it. The CNN part is not shared for the moment. It's actually kept centralized. Okay. So I will describe three cases. Let's say the simpler case is the Google Speech commands. That's a very simple 2-layer, 3-layer neural network where you have 35 labels, classes at the very end, and we have 4,000 neurons per layer. Okay. For this example, we try to not use GPU, just to make sure that we can actually do this with CPUs. We tried the VGG network on CFAR 100 and the full ImageNet. I want to highlight this with the full ImageNet because it is the full 14 million images on 21K categories, because ImageNet usually it is in 1K categories, and I'm not sure whether there is any result on 21 categories. If someone knows something, please send it back to me. So this is actually the real thing. This is how I want to consider this, because having 21,000 categories at the very end, believe me, because it is at the feed-forward, like it's at the very last layer, and you have full connectivity, this takes a lot of memory, and you cannot easily share this information over a network. So you have to do something else. And we also have the extreme classification problem, which is not related that much with neural networks. Again, we use it we solve it with a neural network, but again, the dimensionality at the very end is like the labels, the classes is at the order of more than 600,000. Okay, so this is really big data situations. And if you just do distributed learning in the classical way, you're going to be like, you have to be really careful how you're going to share information. Okay, so the current limitation, going back to Dimitris, is that we know how to do it very well with the fully connected layers. So we tried several things with convolutional layers. One of the things is, yes, to split the filters. There are some other papers where they actually split even the weights within the filters, which does not make sense to me. But actually, we have 2 students working on this, so I'm quite confident that we will get to a solution that at least does not hurt in terms of accuracy. This is what's the problem, that while I'm going to show examples that we do not lose in accuracy, with CNNs, we actually lose 1% in accuracy, but we accelerate a lot. So we want to fill the gap of this 1% just before we actually publish this. Okay. And I just want, for the sake of what I'm going to say today, actually the full connected layers take more than 70% of the parameters, which is what it is actually shared. This is what actually takes a lot of time in the communication. So keeping the convolutional layers centralized is not a big deal for this type of the problems that we have here. Okay, so some scalability issues here, scalability comparisons. I compare it only with the data parallel model, not the model parallel, because it is more tricky to set it up, to be honest. The data parallel is quite simple, that's why it's famous. What you see here with the blue curve, okay, x-axis number of nodes, in this particular case is the number of CPUs. Y-axis is actually the speed up in terms of time per iteration, let's say. This is what we have as a speed up, time per iteration, okay? So on the x-axis, the blue curve, the deep blue curve is like the data parallel. So you don't get much of a speed up. You can actually do local SGD on top of the data parallel, and then you have the 3 curves on top of the blue curves, and you see the reddish curves, which are actually IST. Okay, per iteration, which is expected actually, because you have less communication, less number of parameters per worker, etc., you see a lot of speed up. Okay, you see that per iteration, I'm going to be much faster. Now the question is, how many iterations do I need, right? It's not like I compare it in the absolute wall time. And of course, I'm going to compare this also with the CNN part, where now you can see that you don't have the same time of speed up, because now you have to wait for the convolutional layers, which are actually common, but still you see a speed up compared to the data parallel. Again, I remind you, local STD is data parallel by doing local STD updates, not just gradient and sharing. You just do some updates and then you share, okay? And you can see definitely like a speed up twice as much as the best, at least as the best in the data parallel, okay? Any questions so far? This is one iteration. This is scalability, doesn't draw the full picture yet, okay?
So can you define speed up? I'm a little confused here.
Per iteration, as iteration is defined per algorithm. So it's like kind of like comparing apples with oranges, but just I want to make sure that per iteration, we really reduce the communication. So one iteration for the data parallel is that I send the data to the workers, they do one iteration, then I send the data back and I count the time. In our case, I just want to highlight here that we really reduce the communication and we reduce the computational time per worker. This is what I'm saying.
So do you have a breakdown of communication versus computation? Because it may well have been the case that computation is what you reduce here rather than communication. The only reason I'm saying that it's only 8 nodes, right? So it could be the case that communication costs are not that high.
In this particular case, we're certain because we have the plots from the AWS and how the communication went, and I don't have it here, but this is actually described like in the paper also, that this is also definitely the most significant part is actually the communication, not the computation.
Tasos, can you qualify it a little bit about the number of iterations in the separate systems? Because you said that you get some interesting speed up with only one step at the separate systems. So do you expect to get something more when you have more steps?
Yeah. I mean, I have some more results to show. So this is just, I'm drawing the picture here. I'm going to give you absolute numbers of how much time it takes to run our algorithm compared to data parallel.
Okay, let's see.
Tasos,
yes.
How do you explain the fact, related to the question of Dimitris, the fact that with 8 nodes, we achieve, let's say, 70 times speed up?
Because you compare things in absolute time. Mm-hmm. Like the time that you need to send the nodes, to send the model over all 8 nodes, okay? Then you compute something locally and then you send the information back. This is what we mean speed up here. Like the communication takes, it's like if it takes, for example, 1 second for the data parallel, we take 1 over the 7, like you do the math in order to say that we're 70 times faster per iteration. But so far I have been saying that maybe I'm doing such an approximation of the problem that I need like twice or 10 times more iterations to get the same accuracy, because I'm not drawing the full picture here. The full picture is going to be in the next slide, where I'm going to show exact times. And I'm not saying that we have full answers in all these questions, because yes, there might be cases where the speed up is because of the communication. There might be cases where the speed up is because of the computation savings. But overall, we're happy with both of them. Either of them, if this happens, then we're happy. And we see that this happens, and for these particular graphs, I know that it is the communication that takes a lot of time.
I think that you can measure both the communication and the computation separately. And
that would be very helpful. Yeah, I agree with you. But this is blended together. Yes.
Okay. One more question. Does the topology of these patches, when you separate the whole system in some subsets, does the topology play some roles? Maybe if these patches are consecutive, one next to the other, or they are interlaced, one somehow inside the other.
So for the moment, by patches, I assume the way we
the subsets of the total number of nodes.
So far, because we claim completely independence between the nodes, the way we split it is not exactly random, but definitely it's random enough in the sense that without replacement. In the sense that I make sure that I split the nodes in a random way, but still in a way that they don't overlap. Now, this is a very good point, because I go back to Dimitris, because he has worked on these kind of things. If there is a small overlap, it might be the case that you can do asynchronous communication. And if the overlap is very small, then maybe you override some of the updates, but you're going to be fine. This is like on the ideas of the hog wild kind of perspective. And we haven't tried this yet, in the sense that maybe we can even remove the synchronization and allow each of the subnetworks to work independently. So,
but I'm still asking something a little bit different. That, for example, if I speak about the topology of these subsets, if you take 1, 2, 3, and then 5, 6, 7, and so on, or you can somehow interlace these nodes one inside the other. They are not simply connected, for example.
Yes. So theory states that it can work either way, but if you stick with the same plan per iteration, then this is not exactly what we're proposing. By interlacing, that's the only thing is it's a matter of implementation. If it is easier to implement something in sequence and then you actually split it this way in some random way, and actually this saves you time, and if you see that this works pretty well, then I would suggest that we do it like in a more principled way. But the main idea is that you actually split it randomly. So there is it does not depend on that.
Okay, thanks.
That's a quick question. So by local SGD, you just mean the unsparsified version, right? Yeah,
exactly. So let me go directly here. A lot of numbers, but I'm going to highlight what I want to say here. 4 examples. Okay. Google Speed's 2 layers, 3 layers, C400 full ImageNet. This is the data parallel case where I do one gradient update and then I synchronize. This is the local SGD where the number of, it is exactly data parallel, but locally you do more local SGD iterations. And this is the IST, our method, right? I have here 2, 4, and 8 nodes. So these are different settings for each of the columns, okay? And I have different accuracies. And what I mean by accuracy here is like the percentage, like the accuracy, 63% and 78%, for example. And I just count the actual time that you need in order to get to this accuracy, okay? So what we actually observe here is that definitely, as you will see on the right-hand side, the IST method actually decreases, for some of the cases, decreases the time that you need as you increase the number of nodes, while in any other case that you will see on the plot, you actually increase the total time as you put more nodes. This is the classical thing that happens in data parallel, that while it states that yes, you have more GPUs to worry about, because you increase the communication by including more GPUs, you actually make the algorithm go slower. Maybe you can handle bigger problems, of course, but you actually go slower. With IST on the same problem, we managed to have cases where you actually, as you increase the number of nodes, you decrease the time that you need. And as you will see for the case of full ImageNet, you will see the tremendous difference between data parallel, local SGD, and IST in terms of number of iterations in order to get to the accuracy that I state here. The accuracy, of course, it might seem low to you, 20%, but I remind you that this is the 21,000 labels instead of 1,000, which is the classical thing to do. Okay, so you see definitely a speed up by just doing what I just described. Okay, and this is actually shown in this plot. This is the same information. Okay, and as you will see that there are cases here, you can see in the purplish, let's say, curves, what we have here, x-axis is the time, the actual time that includes computation and communication. The y-axis is actually the test accuracy, not the training, the test accuracy. And we have in blue, which is the data parallel, and you can see the other colors is like quite arbitrary, but the purplish, let's say, is our method. And as you can see, these curves are more left, meaning that they get to the same accuracy with less number of time. And as you will see in many of them, as I will show also in the next slide, you get better test accuracy. It goes above the data parallel. Okay, and this is what I want to stretch in the next slide. Because so far, again, I haven't drawn the full picture because someone can have the question, yes, you can get to a specific accuracy faster, but it doesn't mean that you get the best accuracy at the very end because you're actually approximating the full network somehow. Maybe you get lower, but faster, right? And this is where I want to get, and this is the last slide here. This is the final accuracies that you get by using data parallel and local SCD, okay? And this is the final accuracies that you get with IST. So you get there faster and you get there better. And this is what actually it's quite amazing. And I would like to understand better why this happens. So you get a better accuracy for all the cases in less number of time. And actually in a lot less, in the sense that you minimize, I cannot say minimize, you reduce a lot the communication, okay? And of course the computation, and I keep saying the computation because I believe it is a key point for the mobile and federated learning applications. If you have a smartphone, you cannot train, even compute a gradient on a full network, you have to go for subnetworks, okay? Now, the last table I want to show is the cases where actually, if you naively say to a system, do data parallel, how it behaves, like this is what I want to show here is on the left column, you have the dimension of each of the layers in the fully connected. So you have 512 neurons, 1,000 neurons, etc., etc., etc. Okay, we denote here the data parallel precision 1, 3, and 5. And as we increase the dimension, data parallel gets back to you and says, I failed to do that because it doesn't fit in my memory. So there is no way I can do it like automatically, you have to do something else. And this is the situation, this is the dimensions, this is where data parallel fails. And actually IST, as you increase the dimensions of the layers, keep increasing, because someone would say, do I need that wide neural network, like the layers to be that wide? Actually, until some point you need it, actually you increase the accuracy. So this is why, for example, wide residual networks is also a good choice to have, because they're quite wide and they show that actually they work pretty well. So I will conclude, because I'm running out of time, with questions. I have not exactly no idea, but almost no idea in optimization guarantees about why these techniques work. I would like to go back to very simplistic cases, matrix factorization, and because matrix factorization is a one hidden layer with linear activations, and I would like to learn why and if in matrix factorization this actually works. Any ideas are more than welcome. Extensions to other architectures, this is what Dimitris actually caught up. I would like to do it fully in CNNs. Already students are working on ResNets and transformants, and we already got very interesting results, at least for ResNets. We do not increase the accuracy, but definitely we reduce a lot the communication. So we can actually go deeper and faster, okay? Now, if we go to the federated learning, and again, I remind to you, for those who don't know what federated learning is the case where you have a lot of devices, and each of the device worker has its own local data, that they don't want to share this data with the rest of the, and they want to reveal any identity to the rest of the workers. Whether IST is a way to do it, whether IST, for example, works on non-IED data. This is what one student actually works on right now. And the final thing, which is related with the grant that we got, I would like to test it on smartphones. I would like to have real smartphones with, I don't know how it is called, tiny TensorFlows or TensorFlow Lite, where they actually use only CPUs. And because you have smaller neural networks, sub-networks, maybe this is the way to go. So I will close with that. I think I'm exactly on time. Thank you very much. The paper is online, and I'm open to questions.
Thank you very much, Tasos. A very interesting presentation. Are there any other questions from the audience?
I have a quick question. That's first of all, really cool stuff. So in the ResNet case, how do you deal with the skip connections? Does it complicate the sampling?
Sorry. The idea is that in ResNet, you have these modules with the skip connections, and actually you're not going to, the subsampling is not going to be with respect to layers, but it's going to be with respect to modules. And so you play with the depth. So you actually play with exactly how the skip connections are used. So you don't always have the same depth, but somehow the depth is preserved. And you combine these things. So these are things that currently the students are working. To be honest, it's not that I know all the details because I've been offline like the past month, but I saw and I asked for their updates and they gave me quite nice results back. So I can report back to you whenever I have results.
Cool, thank you. Great stuff.
So that's one more question. So yeah, I'm wondering if you had the chance to compare with like all reduce or ring reduce. And the reason I'm mentioning ring reduce again is because they don't reduce computation in any way, but communication is reduced to a constant factor, basically essentially the same as yours. So I'm just wondering, you know, if communication is the only thing that you care about, this could have been a useful comparison to have.
May I answer with a question? Can you describe me a little bit more what is ring reduce exactly?
Yeah, so ring reduce is if you have P workers, it's a order P round communication scheme where essentially you split your network in P parts or whatever, and then you communicate from worker 1 to worker 2, one of the blocks, from worker 2 to worker 3, another block, and so on. And you kind of have to rotate this process for like P times so that the entire network is communicated everywhere, right? So in terms of communication, it's like easy to prove that this has, you know, constant cost. You communicate, you know, your full network once, and algorithmically it's equivalent to SGD, like you don't lose anything. So like if communication is your only goal to reduce it, I think it would be a valuable experiment to have.
So again, one question, would that be easy to set up or is it something that you need? One of the components that we have.
If you run PyTorch, for example, and we have it, I can share the code with you, but you know, you can basically use OpenMPI for the communication protocols. And OpenMPI is basically, you know, supports ring reduce. But yeah, I'm happy to like share the code for that if you guys do PyTorch.
Awesome.
Stuff.
First of all, I need the code so that I send it to the student and he can check it. Second, if it requires, let's say, a little bit more engineering rather than saying like to the what we actually do is very similar to the data parallel. The only thing that we add on top of that, and to be honest, the actual implementation of the method that we have and what you have seen is a distributed, and maybe this is what a distributed parameter server. Maybe this is exactly what you're actually describing, where actually each of the workers is at the same time parameter server, and it is responsible for a subset of the network, and they actually share it together. Maybe it's the same thing, but that's not the case why we went faster, because it's not just sharing, it's actually you get faster and better in accuracy. So something else is actually happening there. But I would like to see the code. Yeah, please send it to me.
Any other question?
So this is George. Great talk. Great to see you too. I was wondering the decomposition of the global network to many subnets. Are there any specific criteria that you use to do that? Was that done ad hoc or based on non-overlapping nodes, as you said, and maybe any insights on how this maybe could be done in any different way in the future?
So very good question. As being a prototype right now, for the moment, we have been naive and say, you know what, how many workers we have? We have 4. I'm going to split each layer divided by 4. And the way to do it is like, as I said, the random stuff, etc., etc. Now, if you have like a lot of workers, imagine that you have a layer which has 1,000 neurons, and you have 1,000 workers. It's not going to work because it will end up being a path from the input to the output where you have only one connection. So the intuition here is that the weak classifiers, the subnets, should be strong enough, and I cannot quantify it right now, such that they make sense as weak classifiers. So this is kind of like, let's say, a limitation of our approach so far. So we take into account the number of workers that we have like available, the size of the layer, and this is the engineering part where you say, do I have to use all the nodes that I have, or should I, because I don't want to end up with a weak classifier which is really, really thin, and it's actually a path from input to the output. It does not answer exactly your question, but it's exactly because I don't have an exact answer right now. It's like we did the most naive and obvious thing, like divided each layer over the number of workers that you have and do this randomly. Now, whether there is a more complicated and more efficient way to do that, yeah, that's open.
Great, thanks.
Any other question?
I see Yanni smiling. Yes, Yanni.
Γεια σας, γεια σας.
Nice work, Tasso. Nice talk.
Thank you. I think we're running out of time or something like that, no?
And I think we have 9 minutes until...
okay.
Okay. So, Tasso, if I remember correctly, you saw that you proved that the 10 stage, the 10 processor, the gradient is unbiased or something like this?
It's not a gradient, how the function propagates forward, like what you would expect the output of a layer to be if you had all the neurons, and what you would expect if the output, let's say, if you can quantify that, is if you had a subset of that, it performs similarly, kind of like accumulating what the full layer would do with like a, let's say, more thin layer. And no, there is no proof right now about unbiasedness of the gradients. And this is what I would like to do as a next step. If you consider, as I said, these problems in a very simplistic scenarios, linear regression might not be the excellent case here, but matrix factorization, because it behaves like a hidden layer, one hidden layer with linear activation. If we can prove something there, I think that would be very, very cool to say that, you know what, even if I do these approximations on expectation, my algorithm will perform well. These are open questions, and that's why I stated as open questions. I have no other information, because it started as a systems plus ML paper. But now I feel like there are more open questions in theory rather than in practice. For example, another open question for me is like, is there a characterization about this distributed dropout intuition behind our method? Like, how does this work as a regularization? And how, in general, there is like, there is a discussion whether dropout should be used with batch normalization. I think there is a paper that says that you shouldn't. But in our case, we showed that dropout with batch normalization works really well. So these are open questions that we would like to answer in the future.
Okay, a thought I made, but I think that it's wrong. All this process that you distribute the parameters and you update separately the parameters, it reminds me of the Jacobi implementation of the block coordinate design. Okay, but I don't think that there is a direct analogy there.
I agree with you, Mr. Thanasis, because in coordinate descent, you first compute the full, you compute the full gradient and then you select your coordinate. In our case, it seems like we changed the model because you first do the subnet. This is a different function that you minimize now, and then you compute the gradient. That's the difference, and I agree with you.
Yes, so it's not so easy.
I asked this question to Jorge Nocedal, and he said, like, good luck with that. So I have no idea.
Okay, any other questions?
One more question. I think I've been monopolizing the questions, but here's one more. So there's like this recent work on the lottery ticket hypothesis that basically says, you can run for, let's say, a few iterations for, maybe 10% of your training to kind of like find a sub-network that if trained to full accuracy, attains the accuracy of the full dense network, right?
I was about to ask that, Dimitri.
Huh?
Go ahead.
What?
I was about to ask the same question.
Okay.
Go ahead, man.
What me and Ines here are wondering is how that algorithm would compare with your scheme. Yeah. So because you could run this like for 10% of the training, find a sparse structure, and then every worker would basically just work on that structure, which is maybe even 10% of the overall weights, right? So.
No idea. Very good question. Maybe that's a question for the student. But is this something that practitioners will use eventually? Like our aim initially was like, I would like to have a practitioner not worry about that much. Like I'm going to give him or her the option. You can do data parallel, but you can also do our methods. You're not going to code anything. You're going to press a button. Like, if this is something that it is general, first of all, I would like to test it, but if this is something that requires a lot of engineering, let's say, but it seems that it does not, then I would like to understand more about this and see whether this is going to be the trend. Like at the very end, the distributed learning is going to be, yes, do only 10% of the iterations and then stick with the subnet. I have no idea, but this is a very good question. Any comment on that, Dimitris?
Yeah, I guess I want to say that, like, I guess it's how easy it is to implement all of these methods. Just like, how many more hyperparameters do you introduce, right? So for the lottery ticket, you have, I guess, 2 or 3 new hyperparameters. For yours, it's probably like 1 hyperparameter, like how you will partition the...
How you split. Yeah, that's the only thing.
So, I mean, yeah, it's in the eye of the beholder. But I think, scientifically speaking, it would still be interesting to see, how they compare in terms of accuracy and communication.
I agree. Let me stop sharing so that you actually see my face instead of, yeah.
Okay. Thank you, Tasso. Is there any other question? I see some other guys, many years, like my friend Yannis. Are you Yanni? George Klyvanitis.
Καλά είμαστε, κύριε Θανάση. Everything is good. Good to see you.
Good to see you, Yanni. Good to hear from you.
Έχουν τα κομμωτήρια και οι μπαρμπέριδες στο Μοντρεάλ, φαίνεται.
Ορίστε.
Κάνει πλάκα ο Δημήτρης ότι δεν έχουμε μπαρμπέριδες.
Ναι, θυμάμαι. Το μαλλί που το άφησες.
Τώρα αυτό είναι πρόσφατο. Έχω χρόνια που είναι κοντό το μαλλί, κύριε Θανάση.
Okay. We have 2 or 3 more minutes before we pass to our last speaker. I would like to thank Tasos. I think, Tasos, you put more questions than the answers you gave.
Which is awesome. That was my task, actually.
Yes. So you are successful in this. So our last speaker is Vagelis Papalexakis. He also got his diploma and master's from this department under the supervision of our friend Nikos Sideropoulos. And now he is assistant professor at the University of California at Riverside. So, Vageli, we hear you.
Sorry, I was on mute. So thank you so much for the introduction. I'm really happy to be among friends, even remotely. Today what I'm going to do is I'm going to try to give a kind of an overview of the research that is happening in my lab recently. So this is sort of the roadmap for today. First of all, we're going to introduce a few things about myself. Then we're going to see 3 key applications of tensors. And then I'm going to conclude with some takeaway messages and a few sort of selling points in case somebody's interested in our department at UCR for graduate studies or for visiting or any activities. And so, first of all, I'd like to wish our beloved department happy 30th. It wasn't too long ago that it was my 30th birthday, so it was fun. So I wish our department the same fun and continued success. And I'd love to be here for the 40th and so on, and intermediate birthdays as well. So a few things about me, even though Mr. Thanasis gave a good overview. So I spent 2005 to 2011 at TUC under the supervision of Professor Sidiropoulos. I did my diploma and my master's there. Then I boarded a plane. I went to Carnegie Mellon, worked with Christos Faloutsos for another 5 years. I spent some summers in the Bay Area, twice at Microsoft Research and once at Google Research. And as of 2016, I am at Riverside in Southern California as an assistant professor. And so I'm going to sort of give you an overview of our recent work that is also based on the foundations that started actually during my thesis work back at TUC. And so this is, everything is connected. So the first sort of stop in our road trip is I'm going to introduce tensors under the lens of graph mining, because I find it to be a compelling and easy to relate application. And we have some nice, interesting results that tie to some modern results in graph mining and graph analytics. And so I'm going to start with kind of like introducing multi-view social networks or graphs, where basically we have nodes. Let's say we have a bunch of friends. And in addition to the fact that we know that those friends are linked to each other, we also have some context about how they're linked. So we know that, let's say, these two friends are Skyping. Maybe these two friends are using Snapchat, which is maybe revealing something that those two friends maybe are of younger age, or maybe they are closer to each other, right? And so understanding the context of communication actually gives us more data, right? And so in principle, having more data enables us to do a better job at understanding the processes happening in that network. And so basically what we would like to do is we'd like to understand, let's say, who is closer to whom, who forms communities and so on, and we would like to leverage all the data in that endeavor. Now, being a linear algebra aficionado myself, the first thing you do when you have a data set is you try to make a matrix out of it. At least that's what I do. And the most sort of accepted way of representing a graph is, in fact, a adjacency matrix, where basically you have the nodes on the rows and the columns, and you have either some binary indication whether if your graph is unweighted or some weight that sort of signifies some importance on the link, right? And that's great because there is actually now a lot of work in understanding how many interesting things are there in the data, right? So if we take a decomposition of this matrix, let's say we take a singular value decomposition, or we take something a little bit more attuned to the realistic constraints, let's say non-negative matrix factorization, we may be able to discover underlying patterns in the data. For instance, let's say in this fictitious example, we have two large blocks, and let's say all those people are friends with all those people, and all those people are friends with all those people. And now we can sort of decompose those two blocks into rank 1 matrices, where now each one of those rank 1 matrices roughly corresponds to a community, right? Where people are closely tied to each other, right? And that's great, but this kind of like defeats the purpose of what I was talking earlier, because in fact, we don't have a single matrix. We have multiple different views, each one of them being represented as a matrix. And if we aggregate, we risk sort of losing important structure. And so basically we are kind of like willingly throwing away data, right? And so instead of aggregating, sort of my personal favorite answer into how we integrated this additional structure is by using a tensor. And sort of a tensor, for all intents and purposes of this talk, is a multidimensional array, sort of a collection of matrices, or a collection of tensors, right? And so a two-dimensional tensor is a matrix. And then the cool thing about tensors is that they can sort of represent a vast array of what we call multi-aspect and multimodal data sets. And multi-view graphs are sort of one of those examples. And there's a long list of really disparate fields from psychometrics to chemometrics to signal processing to machine learning and data mining that have been sort of leveraging tensors and in a good sense rediscovering their power in sort of using them for applications in those fields. And to me, that is a fascinating sort of fact in and of itself, because that points to some inherent sort of universality of why it's a useful proposition to incorporate multiple views or multiple modalities in the data into your analysis. And so sort of a shameless plug, just right when I get everybody sort of interested in tensors, we have two survey papers out recently. Both of them are actually co-authored with Professor Sidiropoulos. This one here on the left is you need some coffee or your favorite sort of poison of choice to sort of really appreciate all the theoretical and algorithmic foundations. And after you read that, you'll actually be able to do algorithmic and theoretical research in tensors. The other one on the right is a little bit more geared towards practitioners, and whether we have an application you're thinking about using some tensor method, that can give you a broad overview of how tensors have been used in sort of data science broadly. And links for both papers are on my website. If you cannot find them, please feel free to email me. I'll send them a copy to you. So now back to business, right? So what are we looking for in that simple multi-view graph scenario? In the similar to the matrix case, we are looking for those blocks within the data, but now those blocks are going to span all three modes of the tensor. So now each block is going to be quote unquote a contextual community, meaning that we not only have information about who's connected to whom more densely, but we also have some information about the means of communication that they leverage. And so that helps us understand what is what potential dynamics are happening in that particular community. Right. Is there a question? Okay. If there are questions, please feel free to interrupt. I'm happy to answer on the fly. Now, the fortuitous fact here is that the definition of a rank 1 entity extends to tensors. And so similar to the case where we decomposed our matrix into rank 1 matrices, each one of them being a outer product of two vectors. Now, let's say we have a 3-mode tensor, we just add one more vector, and this is the generalized outer product, and this is basically a rank 1 tensor. And so that is great because we can now extend the notion of decomposing the tensor data into a sum of rank 1 things, each one of them being a fundamental block in the data. And the most widely used, potentially most widely used tensor decomposition, which does exactly that, is the CP or parafac or canonical decomposition. It has many different names because it has been sort of rediscovered or proposed multiple times and by people who sort of were independent. So again, that points to the universality of having to decompose a multidimensional entity into a sort of a sum of its elementary pieces. And so what I have here, this is the tensor. So this is, let's say, the user means of communication tensor. And each one of those triplets of vectors, affectionately called chicken feet by my advisor, and now this actually has passed into infinity into our survey paper, is a sum of those rank 1 tensors. So basically, we can write this part here, this sum of our rank 1 tensors, as this L tensor here, which is sort of a low rank tensor. And we can also sort of assume that we have another part here, which is sort of high rank, sort of non-structured or uncovered dynamics or noise, right? So basically what we try to do is we try to minimize the loss function between the model and the data. People traditionally have been minimizing the Frobenius norm. Sometimes if we have count data, then usually it's a better thing to minimize is the KL divergence, because that assumes a Poisson distribution on these errors here, especially when these errors are sparse. But we're not going to we're still going to stay on a higher level than this. Now, how do we understand this decomposition in the context of the application? Let's take those A vectors, put them together in a matrix, all the columns of a matrix A, right? So now this matrix is the number of rows is the number of users, and the number of columns is the number of components that we have decomposed the tensor to. And each row of this matrix, let's say we take this row, let's say we take a matrix, this is MATLAB notation, Cartman spanning all the columns. This is going to give us sort of the embedding of this user or this node into what we would hope would be a community space, right? So this R-dimensional space, we hope it captures all those blocks that roughly correspond to communities. And this is basically how we can use this as an exploratory tool to understand partial or sort of complete membership of every user to every community. Now, a natural question that usually arises at this point is, how do you choose this rank R? And in fact, I'm not going to talk to you about this, but esteemed member of our lab, Yorgos Tsitsikas, who's going to give a talk tomorrow, will spend his talk, or big part of his talk, talking about different ways in which someone can go about discovering the rank, or rather the low rank of the tensor. And so I'm going to defer to that. Even in the lab, if somebody's looking for the rank, they just call Yorgos. But I decided to not put his phone number since this is broadcasted on Facebook, so you know, we don't want to have any adverse effects. So let's see an application, right? So this is quite earlier work, but this is in fact the first work that tried to do this thing, meaning express a multi-view graph as a tensor and then use that as an unsupervised community detection method, right? And so what we have here is a academic graph, and we have three different views. We have the nodes are researchers, and the communities are research communities. So let's say database community, AI community, and so on. So the first view is who cites whom, right? So people, if this person cites that person in their papers, there is a link. The second one is who co-authors papers with whom. And the third one is who uses similar terms with whom. And you can see that there are different facets of how an academic sort of relationship can be captured in each one of those views of the graph, right? So what we do is basically exactly what I showed you in the previous slide. Take those three slices, make a tensor out of it, do the perfect decomposition. We kind of cheat because we know the number of communities here. So this is given to us, but this is sort of the definition of the problem. And so we decompose into the number of communities. And then what we can do is a very simple thing. We can take the vector, the embedding of each user, or each researcher rather, and then we can take the argmax of that vector, assuming that we have non-negativity constraints, and that gives us an assignment to one of the R communities. And in fact, this actually works much better in terms of normalized mutual information, which is a sort of a widely used measure of success in those assignment problems, than any smart two-dimensional way, of doing things. So we just found what was the state of the art in two-dimensional sort of matrix-based methods, and in fact, this simple tensor method outperforms all of them. And of course, this was back in 2013. This now has been superseded by other methods, both by us, but also by other people. But this was the first indication that, you know what, having some higher order structure in those different views actually pays off in terms of getting a better detection accuracy in your communities. And so that was the take-home message then. Now, in order to talk to you about how we bring this to the future, or rather to the present, to the neural network dominated present, I'm going to have to take a detour in our sort of road trip and talk a little bit about word embeddings, which is sort of, again, this has been here for a few years, but this is something that is now bread and butter of anybody who's doing anything in natural language processing, where basically the idea is you have a bunch of words, you would like to represent each one as a vector. And the way that this was proposed back in 2013 at NeurIPS to do was to train a very simple neural network, which we call the skipgram, that has one hidden layer. And the input is in basically one word. So you have, let's say, 1,000 words. You have one hot encoding where basically you light up only the word for which you care about predicting something. And then the output is a probability vector that tells you which one of those 1,000 words has high probability of being in the context of that particular word. And so by training this neural network, a fortuitous byproduct is that we are learning a vector representation that respects sort of contextual similarities. And so that space, that embedding space that is learned, actually has those really nice properties that, you know, if in a nearest neighbor query, you get words that actually mean similar things. And so the poster child of examples is, let's say, taking the vector for king, subtracting the vector for man, adding the vector for woman, and then the nearest neighbor vector in that space is the vector for queen. And there's a bunch of other examples like that. Now, those embeddings more or less exist to this day with different bells and whistles. One thing I would like to point out is that there is actually a result that shows that we don't really need to use a skip-gram neural network. We can actually factorize a matrix that holds point-wise mutual information between the target words and all the context words. And that factorization, in fact, gives us the same embeddings, right? And so basically, we can use factorization to get those embeddings in one way or the other. So that's what I want you to remember at a high level. And the citation for that is down here. It's a year after the original Word2Vec paper came out. Now, going back to graphs, those word embeddings inspired node embeddings, where now we want to get an analog of what is a context of a node. It's the neighborhood of the node. And so we would like to make sure that we embed the nodes in a Euclidean space that respects similarities of neighboring similarities of nodes. And so how this is done, we're not going to go into much detail, but there's two variants. The first one was Deep Walk by Brian Perozzi, which is really influential work. And basically the idea is for each given node, you do a random walk, and then that's how you obtain the context, quote unquote. And then you do basically the same steps as you would do in Word2Vec. And so now you have what we call either Deep Walk or Node2Vec that basically do that business. Now, there is also a work that says, what if we have node features? And this is where the factorization comes into play. So this paper from IHCAI 2015 says we can actually introduce features for the nodes by if we view the Word2Vec as the factorization of the point-wise mutual informations, or the Deep Walk rather, which comes from the previous result, we can actually inject this T matrix, which contains some node features. And so now we are using basically node embeddings that also respect features of the nodes, right? And so this is kind of like the state of the art in node embeddings with a few bells and whistles now. Now, where do tensors come into play? So here's the idea. This is work that we did a couple of years ago with Saba, who was my sort of shadow advisee in UCR. And the idea is we have the adjacency matrix, which is this Y matrix here, which is the regular graph that is given to us. And we have a feature matrix, which is nodes by features, right? So what we want to do is we want to create a graph that captures similarities of nodes in that feature space. And the simplest thing you can do is you can take a k nearest neighbor graph in that feature space. And again, k is a parameter we sort of exhaustively experimentally evaluated, but this gives us the Z adjacency matrix. So now we have two adjacency matrices that capture different similarities of those nodes. One of them being the organic sort of link similarity, and the other one being similarity over the features. And we stack them one after the other, and we get a tensor. Now, if this Y was a multi-view graph, we could just simply have multiple different adjacency matrices, and we would tag this Z matrix in the back, right? And so now we have a tensor, and what do? We can decompose it again using the CP decomposition, and this is going to give us, again, the embeddings that we would like. And in fact, this works really well. So these are the state-of-the-art sort of node embeddings. This TADW is the one that uses feature information. And for different graphs, Wikipedia, web knowledge base, and sites here, we observe almost across the board that we have a gain over those traditional methods. And so this, I would sort of postulate is because the tensor is able to leverage, again, the higher order information across those two different types of graphs in order to get a better, sort of more high quality embedding that can work better in downstream tasks. And so that's one nice sort of result that brings tensors back into the game, even though there's still much work to be done. Are there any questions at this point? Or
I have a quick question here.
Yeah.
Vageli, 1 second. Basically, about your metrics of evaluation here, how do you evaluate? What's your main metric for evaluating here?
Yeah, so I kind of skipped that. Thanks for bringing me back to discipline. So basically, we use those embeddings in a downstream task of node classification. And so you use them as features, basically. So that says that those features generated by this embedding are better features in the node classification or link prediction task. There's multiple different standardized tasks that people use those embeddings for. Same as in natural language processing, people use those word embeddings to solve, let's say, GRE problems or analogy problems. And so whoever does better in this task, whoever embedding does better in this task is sort of assumed that this is a better embedding, which makes sense, but also is kind of like a slight leap of faith that you have to make. But this is how all those things are evaluated.
Are these mostly binary classification problems that you're using here for evaluation?
Some of them are multi-class because you're classifying community, right? So you may have like 5 or 10 communities, right? But nothing to the effect of like, thousands classes or anything like that you would see in an ImageNet.
Right. Okay, thank you.
Vageli,
yeah,
that also explains why, it's 50% accuracies, right?
Right, yeah.
It's not binary. But the question is, more general question, more general than your work. If the ultimate task is to do classification, right? Why not train an end-to-end, classifier, whether it is a neural network or whatever the heck have you? That would be sort of the question.
Yeah, no, that's a great question, and that goes back to the leap of faith that I talked about. I think the argument against that is that I can think of multiple ways that one would not want to do that. One is that you may not have enough data to train end-to-end, and so you want to sort of have a good set of features that give you a head start and maybe train a more simple classifier in the end. The other one is you may want to have a sort of a universal representation of your data that sort of respects basic similarities of the entities in the data that now can be sort of used for multiple tasks at the same time. And so that kind of like goes away to some extent if you train end-to-end. But it really depends on the task. And so my interest personally is not on the downstream task. My interest is on the exploratory analysis. And so when you do exploratory analysis, then sort of explicitly you want a representation that retains all the good stuff in the data, but is simple and hopefully interpretable. And so, but this is a harder thing to evaluate, and it's really application dependent. But if you cared about optimizing the accuracy given enough data, it's a no-brainer that you train an end-to-end network and it does the job. Or some sophisticated sort of supervised approach.
Thank you. And are there, no, I get it. I mean, especially the data part, right? If you're in the data starved regime, then you may not be able to train well an end-to-end solution. But the other question, are there any guarantees that you are actually preserving the geometry or, in what you do?
That's a great question. Well, I don't think there are solid guarantees, at least for those methods. There is work on embeddings that try to impose a certain geometry on the space. But again, with that comes higher price in what you pay to make them. Yeah, I'm not familiar with guarantees of preservation of the geometry exactly. So most of the arguments are preservation of the local proximity of nodes. But then whether that is something that you need or not, it really depends on what you're trying to do with the data, right? So it's hard to preserve the entire structure of the graph in a single vector.
Yeah, okay. That's a longer question after you.
Yeah.
Right. Thank you, sir.
Thank you. All right. So moving forward to another sort of kind of view, time is also a view, right? So time also gives us information about what's going on in a graph. And so for instance, let's say you have people publishing at different venues over time. You can understand, let's say, communities that form or disappear or become really popular and so on, right? Now, as an example of a time-evolving community, so that I give you sort of, this is, again, probably the mother of all examples of time-evolving graphs. So it goes back to our work with Professor Sidiropoulos back in Chania, where basically we have a employee by time graph, time-evolving graph of the Enron company. And if you don't know Enron was an energy company that did a few things wrong. And as part of the ECE investigation, all their communications are now public domain. And that's why everybody likes analyzing this graph, because it has everything in it. People have found affairs between employees in those emails. It's crazy, you know. But what we have is sort of a redacted version of that, where we see communications of employees over time. And what you can see here is, let's say you take one of those blocks, you have A, B, and C. So A and B are going to give you sort of the people who are involved in that community. And so you can go and look at those folks. And what we've done is we've looked at those people's affiliation, which department of the company they're in, right? So legal, executives, and so on. And this C matrix now is going to give you a time series where the intensity is relative to sort of what is reconstructed in tensor. But if we sort of normalize it, this tells us the degree of intensity of that community for that given particular point in time. And so this is kind of like, can be plotted like this. And you can see, for example, interesting things in this particular time evolving graph, where now this executive and government affairs, for instance, department of the company started going crazy when the investigation began. And so you can kind of like see spikes and try to correlate them with outside events and so on. So that's like a use case of why, you know, introducing time in graphs is something important, right? I'm not gonna sort of talk more about examples here, but I'm gonna touch something that is an exciting result that we have recently with one of my students. And I would like, and again, this is not even the end of it, is scratching just the surface of what's possible. So given that we enrich in time, sometimes data comes as a stream, right? So imagine you are Facebook and you have your graph being updated every second or every microsecond, you know, because things happen all the time, right? So how do you maintain a particular decomposition and incrementally update it when you get new sort of graphs, new slices, or new batches of slices, right? So that's sort of the tracking the decomposition example. And there's classical work by Professor Sidiropoulos. There's also more recent work. And we've also done some work where we basically use different kinds of sketches to lower the computational complexity and memory requirements, where we now update only the sketch when a new part of data comes, and this helps us scale, right? And so we have two papers. I'm not going to describe them in detail because that goes beyond the point I want to make, but one of them is using random index sampling, and the other one is using random compression in order to sort of maintain sketches and update them on the fly, thereby sort of scaling. Now, all work, or I guess most streaming work, including our own, assumes something very central, which is that I have some data already decomposed into R components, and then I got some new data, and I'm expecting to see all the same communities, let's say, in this new data, right? So the rank of the existing decomposition should be the same when I tack on the new updated data, right? And so that's something that maybe not entirely true in all realistic scenarios, where maybe when we have new data, some of the communities in that case have disappeared, maybe some new communities have emerged. And so merging everything into the same factors may actually result in suboptimal approximation, and even worse, in suboptimal explanation of what's going on in the data. So what we have here, I'm just gonna skip that a little bit, but we have a paper out at ECML PKDD with Ravdeep, where basically we are trying to formulate that problem and trying to find a solution to tracking that and alleviating that. And we see evidence that doing that actually helps. The name of the algorithm is Seek and Destroy, because Ravdeep and I made a bet that he has to graduate after he makes every method of his in every paper a Metallica song, but he didn't know how many Metallica albums there, so he may have lost that bet. So he has to write a lot of papers. But the idea is the following. At every step, we try to understand what is the rank that we already have, and what is the rank of a batch that we've accumulated. And in any case, we try to do a N to M, if the rank is different, matching of components based on sort of similarity. And this way we conclude whether there are new components, old components, and so on. And we have the concept of the running rank, which is how many components are active. And then we have the concept of the full rank, which is how many components we have seen in the entire lifetime of the stream. And so now this is kind of like a new notion, and we were a little bit puzzled how we test it. So in order to test it, we first of all simulated data. So we start with all those are synthetic tensors, where basically we start by 100, 100, 100. This is the original tensor. And what we do is we batch it and we break it up. And each batch starts with initial rank 2 and grows up to 5 or 10. And in some cases, we decrease. And so by increasing the batch, the rank as we add batches, this is the actual rank that we detected. And this is the actual rank that was there. And this is the rank that we detected when increasing and decreasing. So basically, by tracking that drift, we're actually able to more or less do a correct prediction of whether the rank has changed and whether we have new or old components present. Now, if we compare against streaming methods that do not take that into account, we have some interesting observations. What I'm showing you here is online CP and Sambaten are sort of two methods that are recent. Sambaten is ours, online CP is not. And what we do is we have two different universes. In one universe, we give those methods the initial rank. So they know it, but they don't know what is going to be the final full rank of the tensor. And then in the other universe, the full rank universe, we give them a really big benefit, which is this is the final rank that you're going to see. And in fact, if we give them the final rank, they actually do okay in terms of approximation error of the entire tensor. But if we give them only the starting rank, they suffer a lot. And so this is another indication of taking concept drift into account actually makes a big difference. And the other thing I wanted to show is that even if we stream the Enron dataset, we chuck it into different batches and we stream it, we actually are able to detect sort of micro components that those other methods miss. And so this is something that we would like to explore further, but there's enough evidence here that there is something there. And of course, the algorithm for now is extremely slow, excruciatingly slow, because it has to take into account a correct matching between different components. But we are very interested in taking that further. I think there's a question in the chat. Let me see. Oh, see you, Pano. Sorry. All right. So any questions at this point? Cool. All right. Oh, yes,
I had a question again. Yes. Sorry for the for the slowness. Maybe we can leave that for the end. But I was curious about the idea of concept drift and whether you think there's a generally commonly accepted definition of the idea of concept drift.
That's a beautiful question. I don't think there's well, maybe I'm guilty of misusing the term, because perhaps a structured drift would have been a better term here. But I guess concept drift in supervised learning is a little bit more well-founded in that it is or covariate shift, right? Those things are, I guess, the same term, right? Basically, the distribution of what you've learned is now shifting to something that is not the distribution that you learned, right? And so here, we're dealing with unsupervised learning, and so there's not much work in formulating that. And so basically, the claim here is that this is concept drift in latent factors of tensors, right? So this is a very narrow claim here, right? But to what extent that has connections to covariate shift, as people in deep learning know or study very well, I'm not sure, but there may be some.
And follow up, do you typically work with, a one-off discrete change, or do you also work with models that try to track a continuous change in models?
So that's another beautiful question. So for now, we're talking about crude changes, but I think there is a lot of value in tracking slower change, because that is actually what is the most dangerous version of drift, at least to my understanding. Thank you.
Thank you.
All right. So we're still in graphs, but we're close to the end of the graphs, and then the other applications are shorter. But one thing that is, again, newish, actually appeared at WWW this year, is something that I'm also excited about, which is, I've been talking about rank 1 components all this time, and I'm really sold on them, and I hopefully sold everybody on those, but sometimes they can be restricted, because when you assume in a graph that you have a rank 1 block that basically sees a full click of all the nodes with each other, maybe with smaller weights, if let's say these weights are not uniform, but there's still going to be a full click that you're going to have to decide what you're going to do with it. And if you want to study a graph, real graphs are not only clicks, right? So let's say we take a knowledge graph where basically we capture facts. So Trump is president of the US, Merkel is chancellor of Germany, Mitsotakis is prime minister of Greece. If we see this as a click in this latent space, then we make the inference that Trump is chancellor of Greece. And this is something that is perhaps incorrect, right? So we wouldn't want to make that assumption, right? Or if we're analyzing social graph data, the way that a social media influencer appears is very different from the way that friends, really tightly knit friends appear, right? So a social media influencer would appear as we call a star graph, which is sort of one node in the middle and has a lot of different nodes connected to it, but there's not much connection around those nodes, right? And so a star graph is very different from a bipartite core and from a chain graph. And so basically there is risk structure in graphs, and we're kind of ignoring it, or we're kind of imposing click block structure on it, right? And so this goes back to work by my academic sister Denai, where what they do is they are trying to express a large graph as a short vocabulary of elementary kinds of graphs. So a star, a chain, a click, and so on. And they in fact find, for example, in the Wikipedia co-edit graph, they find stars being the most predominant structure. And then usually bipartite cores are edit wars, where there's a disputed page and somebody goes and edits something, and then the other group goes and changes that edit to their favorite thing, right? And so there's a lot of stuff happening out there, and we may be missing out on it. And so how do we do that? Because we still like tensors. So how do we do that in tensors? One idea that we started exploring is to take those rank 1 terms and start feeding them a little bit and get them a little fatter. And so basically, instead of having vectors on the first 2 modes that are representing the graph, we want to have rank L matrices that are sort of able to express, if we multiply them out, able to express more rich structure. And so if we have a click, then this one is perfectly fine. Rank 1 is perfectly fine. If we have a star, then we need a higher rank to capture that. And so this has a name. This is called block term decomposition. And in fact, this is a special case of it, which is the LL1, because we have rank L, and 1 here. And we use that to extract rich structures from a graph. And then we sort of map them to existing vocabularies, and we study the graph this way. So this is basically, the hope would be that, we have a graph that has all sorts of things in it, and it's a time evolving graph or something else. And through this, we are able to extract those rich structures, and we can now study the actual structure of the community and not impose any artifacts on it. And this is work by my most senior student, Ekta, that appeared this year at WWW. And just to give you an example, in order again to test it, we create a graph where we inject structures that we know, and we see whether, if we increase the L, the complexity with which you can capture the structures, whether that improves our ability to capture them. And in fact, for a decently large L, we're able to capture stars in the graph. And of course, we do pretty okay with clicks, even with a smaller L. And so this is sort of again, this is the beginning paper. We're interested in exploring that in various different ways, but this is something that I'm also very interested in moving forward in the future. And now, sorry, is there, yes?
Yeah. So in your experiments here, you have the same block rank for each block term?
So that's a great question. Yeah, so for those experiments, yes, but one of the things we want to do is we want to automatically determine the block rank for each one of the components. And that's work we're currently doing.
Okay, thank you.
Thank you. Now, in the remaining of the time, I'm gonna spend some time on two new applications in my lab and give you some exciting sort of preliminary results. One of them has to do with gravitational wave detection. And so more than 100 years ago, this fellow here said something along those lines. Basically, if you have two accelerating masses, then those are gonna emit what we call gravitational waves, which are ripples in the space-time that travel through space with the speed of light. So imagine those are two black holes, really massive black holes, and they're dancing around each other. Their dance is actually creating a ripple in space-time that we can actually hope to basically be able to detect. Now, we were not able until 100 years after Einstein predicted that, and we were able to detect them with interferometry, laser interferometry. So LIGO is the Advanced Laser Gravitational Wave Observatory, and there's two of them, one in Louisiana and one in Washington State. And basically how they work is they use traditional laser interferometry, but on steroids, in order to detect those really minute disturbances of space in the order of 10 to the minus 21. And the idea is you have a splitter here, you have two mirrors here, here, and the laser goes back and forth. If there's no disturbance, the lasers cancel out, and here's what you observe. If the wave comes from this way, then there's gonna be a disturbance here. So the two lasers are gonna start sort of commingling, and you'll see some interference here. And so this is a sort of engineering marvel, how we can detect those disturbances. But back in October 2015, LIGO was able to detect the first sort of such gravitational wave, which was two black holes that were sort of accelerating around each other until this point here where they merged into a single one. And this is the actual signal overlaid by the predicted signal from Einstein's equations. And this is from the two different sort of observatories, with obviously shifted by the speed of light that the wave takes to travel there. And this is a nice way we're looking at them, which is basically a short time Fourier transform spectrogram where we see the frequencies and over time, right? And so this is now sort of, why is this important, is because this can help us understand and study objects that do not emit light. So black holes do not emit light, they emit gravitational waves. There's other things that emit gravitational waves that we have no idea about, which they call unmodeled sources. And this is now a new lens to the universe. And this is really exciting. Now, a big problem is that there's a lot of noise. So those detectors are, for instance, the best seismometers in the world. They can capture an earthquake in Sydney, for example, right? There's there's a lot of noise. And the most particularly bothersome kind of noise is called glitches, which is non-Gaussian transient noise sort of artifacts that look like useful astronomical signal, but they're not. And sometimes they can actually occlude useful signal. So this is the only neutron star merger that we've observed so far. And this really nasty thing here is actually a glitch that we're lucky because the neutron star actually is a longer signal. Otherwise, this would have been missed, and we may have missed on this phenomenon, right? And so glitches are a big problem that as the sensitivity of the detectors is improved, and as we get more detectors, so there's now in Italy, Virgo, there's gonna be one in India, one in Japan, and so on, the number of glitches is gonna go up, right? And so we need to do something about that before we want to do something about the astronomy itself. And so how do we turn this into a machine learning problem? So there is this project called Gravity Spy, which is a citizen science project where basically folks are looking at different spectrograms of different glitches that are morphologically different in the frequency time domain, right, in this picture, really. And basically what folks do is they turn this into an image classification problem where you have sort of those, I think, 28 different classes that they have identified, and people sort of label them on the web. Now, there's multiple issues moving forward because you see here that there's a lot of skew. And so we have some glitches that are very rare, but potentially damaging, and we don't have enough data for them. And also the fact that we're trying to sort of cast this problem as a fixed number of classes problem also presents problems, because how do we know that we won't see new phenomena of glitches arising that we don't have any name for, right? But let me show you what the state of the art is and how we go about dealing with that and how we go moving forward. So state of the art is basically using deep transfer learning. So the idea is we have a convolutional neural network, and basically this part here that has the convolutional filters and so on is broadly construed to be the feature extractor of the network. And then in the end, we have what we call the fully connected layers, which is the classification layer, right? So now what we do is in deep transfer learning, we keep this part here, which has been trained in a data set with ample data. And what we do is we replace this fully connected layer by another layer of our own choosing that has the output to our own classes. And we fine tune either this last few layers or the entire weights if we have enough data to do that. But basically, this is how we transfer those learned weights into a new task. And so the state of the art in Gravity SPI is basically we have a deep neural network, the VGG19 in that case, but this is kind of immaterial because you can take any state of the art ImageNet CNN. And what we do is we initialize it with ImageNet learned weights, and we just adapt the fully connected layer. And this actually, having enough data, works pretty well. Now, the problem is if we throttle the number of labels we have, let's say that instead of having all the labels, we have 10% of those labels. And we see that a lot of classes, you know, this is with all the labels, this is with 10% of the labels, the F1 score for those classes actually suffers, right? And so we cannot really do proper transfer with those classes. And so that's where we wanted to investigate whether we can actually help boost this feature space using tensor decompositions. And in fact, first, this is work by my student Rutuja, and in collaboration actually with Barry Barish, who is former director of LIGO and one of the Nobel laureates for the detection of gravitational waves. And so this is some preliminary work that we've done, where basically first, we're looking into the structure of those glitches in an unsupervised way. And in fact, we see that, for example, the extremely loud glitch that Gravity SPI has determined is in fact 5 different things. And as you see here, there's very morphologically different kinds of structures showing up here. And so now we see also in the entire glitch space, we can see that if we do a unsupervised tensor decomposition, just vanilla non-negative paraffect decomposition, we actually get decent separation of morphologically similar things in the frequency time spectrogram plot. And that gives us some confidence that a tensor decomposition is actually a good way to represent that data in that feature space. And so what we do is we take the good old VGG19 trained on ImageNet weights, and we take a paraffect decomposition of those glitches as well, and we use the glitch to latent factor matrix as an augmented feature matrix. And we put those features together, and this is sort of the combined feature representation. We train a new fully connected layer, the classification layer, and now we have our output. So basically this part here is using a vast amount of unlabeled data just to compute a representation that then is fed to augment the representation that we get from the VGG19. And in fact, if we do that, this is for different ranks, different glitch classes, and with the green color, it represents classes that were boosted in terms of their accuracy with respect to the 10% labels. And so that shows that actually using those features alongside those VGG19 features can actually help us bring up the accuracy, even in cases where we have extremely few labels. And of course, that was really preliminary work. We presented at a workshop at KDD last year, but we keep working on this problem in many different ways. That I think there's a question before I proceed, because I hear something on my, or.
Vageli, what is the third mode in this case? Is it the glitch instance?
So the third mode is the glitch instance, yeah. And in fact, because they use a RGB representation for for the image classification, we actually have a 4-mode tensor because but we don't have to. We can have just the frequency or the value of the spectrogram there.
Thank you.
And Vagelis, yes. Just one quick question. Awesome talk. The labeling of the data has been done by domain experts, essentially?
Well, not necessarily. It's a citizen science project. So basically they tell you this is what this glitch looks like. If you see things like that, then label them as such.
Okay. And has anyone tried, instead of applying learning on the images of the spectrograms, going directly on the raw data, the space-time data?
It's a good question. I think they have. The problem with the raw data is that they're very high frequency. And so it's, there is work that uses the raw signal, but it is a little bit, in terms of glitches, at least in the main channel, it is not as efficient because the data is just too much. But this brings me to what we're doing now, which basically is we actually care about fixing those glitches in LIGO, right? So we don't care about saying this looks like this, congratulations, this looks like that, great job. But we care about identifying why and how, if there's a mechanism that caused this, right? So what we do is we now take the entire set of auxiliary channels that LIGO is monitoring, everything, all the instruments, they have like thousands of channels, and we're looking into whether a small subset of those channels can actually predict what kind of glitch it is. And that would also help us identify or make a story of how and why this happens and trace it back and hopefully fix that in the detector. And that can help us go into separating astronomical useful science signal from noise and can help us sort of, let's say, cluster unmodeled sources or signals that are from the same unmodeled source for which we have no idea what Einstein's equations would look like. And also this has some implications of tensor methods for augmenting deep transfer learning, which is something that we're exploring separately as well. Now, the last thing I want to say is going to be shorter. And so I think we're pretty much on time, but it has to do with adversarial machine learning and how tensors can help have efficient and effective defenses in adversarial machine learning. And so the idea is, you know that all those things are very successful. Tesla is actually using computer vision, CNN-driven computer vision, to my understanding, for understanding the road and the signs and so on. And you have things like that, right? So you have things where you have an image and you perturb it in a very smart way, and then you have the classification outcome being entirely off, right? And you have stickers on a stop sign that actually throw off even the most accurate CNNs. And in fact, this happened in February, where basically a Tesla would have been caught speeding if there was a police officer there, was fooled to think that he could drive 50 miles per hour because of a sticker on a speed limit sign. So this is not just an academic curiosity, but it's going to actually, be costly in the real world. Now, how do we defend against this? So basically, what is the problem? The problem is we have X, which is the clean instance, this adorable panda here, and then X prime, which is the perturbed instance. So we do this delta, which in this case, this is here, and the goal is for the attacker for the classification outcome of the original to be different from the perturbed, while respecting the similarity of that image in some norm, and typically also would like to respect that in the visual perception of a human, which is kind of a deeper, more philosophical question. And one defense mechanism that we are interested in, not the only one, but one that we are interested in at this point, is to pre-process the potentially attacked instances in order to bring it back to the same classification outcome by applying this function G that brings, hopefully, sort of alleviates the effect of this delta. There are also other approaches that train the network using adversarial examples and make it more robust, but we're assuming that we have no access to train the network. We want to process the image per se, right? And so this work came out a few years ago by my older academic brother, Polo Chow at Georgia Tech, and has a really interesting observation. They observe that those attacks are of high frequency. Basically, they only appear in the high frequency spectrum in the discrete cosine transform that one would take to make a JPEG compression of that image. And so if you compress further those images using JPEG, then actually the attack goes away. And they actually show that in many different ways in the paper. So the takeaway message is that those attacks somehow behave in a special way in the spectrum. And our suspicion was that they actually behave in a special way in the quote-unquote singular value spectrum, if that was basically the latent spectrum of a tensor. And so what we do is we stack multiple attacked images together, we create a tensor, and we take a low rank factorization of that tensor, and that actually results in state-of-the-art restoration of the accuracy with almost as fast speed as the JPEG compression. And so I'm not going to go into details because I'm running out of time, but we tried multiple different models of tensors, and TensorTrain actually turned out to be the most prudent for this case because we wanted to stack multiple tensors on top of each other. But here are the results. So basically, this SLQ is the state-of-the-art in JPEG compression. This is the runtime, and this is the accuracy after the application of the defense. And you see here that this TensorTrain with 4-mode tensor and various hyperparameters gave us the best accuracy, but even the one that is closest to the speed of the fastest state-of-the-art is actually better in restoring the accuracy in the state-of-the-art. And so that tells us that there is something useful to be gained by taking this low rank factorization that also does not distort the images too much. One thing before I finish is that we also saw the same phenomenon in attacks in graph convolutional networks, where now the perturbation is on the edges between different nodes, and now the target is to misclassify a particular node. And in reality, one would say by fake followers so that they're classified as very popular or whatever. And this is something that it's a mathematically studied attack at KDD, actually best paper award at KDD 2018. And so we show that exactly the same thing actually can alleviate attacks in graph convolutional networks by taking a low rank factorization of the graph. And then if we stack multiple graphs together and we take a tensor factorization, again, we see the same restoration of accuracy. And those plots are basically fraction of nodes that are correctly classified and fraction of nodes are incorrectly classified. So everything that is below this line is incorrectly classified. And you see that this is the full attack, and this is the restoration. This is clean, and this is how much it's restored by different ranks of the factorization. And again, that's a really hopeful message that perhaps there's something universal in how those attacks behave, and that may be hinting to a universal solution, perhaps. And the last thing is, well, just to conclude and give some closure to the work, most of my work has focused on unsupervised exploratory analysis, and this is by no means solved. There are a lot of challenges. For example, what structure is in the data? Is there structure in the data to begin with? How much of that structure is there? What model should I use? And then this question actually is a paper by Richard Harshman, who was the inventor of parafact decomposition. There's a paper by him that is still relevant to this day, which the title is, How Can I Know If It's Real? And so this is actually a really nice read that gives some qualitative answers to those problems. But again, what I'm interested in is also tensors in this brave new deep world where what is the interplay of traditional tensor methods and deep learning in, let's say, augmenting the spaces of features or defending against attacks, right? And so this is kind of like where I see the state of the field right now. And with that, just a few words about potentially folks wanting to come at UCR. So we are actually growing fast. The department has now 38 faculty members, 2 of which are called Vagelis. So you're never going to find that anywhere else in the world. And we have centers for data science, cybersecurity, spatial data. That is the view from my office. And you can also find snow in Southern California. So, it's kind of like Hanya, just hotter. One thing is very exciting that we just got this big $10 million grant from USDA and NIFA, which has to do with precision agriculture and using AI to advance sustainable agriculture. And this is going to be for 5 years. And there's going to be a lot of work also pertaining to tensors and their interplay with deep learning and so on, and aimed at both understanding farm management in the precision agriculture way, as well as pest detection using AI. And some beautiful pictures just to convince you to come visit me. If you've seen Kill Bill, that's the beginning of the movie. And some rank 1 coffee for you all. And thank you for your attention, and I'm happy to answer any more questions.
Thank you, Vagelis, very much for this nice talk. Are there any other questions from the audience?
So I have a quick question regarding the defense mechanism. So there was a paper by Carlini, I don't know who else, but definitely Carlini, 2018 ISML, and basically, you know, they studied a lot of pre-processing methods, essentially proving that optimization-based defenses that take into account optimization-based attacks that take into account the defense are basically very strong. So if I, as an attacker, know your defense mechanism, especially if it's a pre-processing mechanism, I can definitely attack it by kind of like designing or taking that into account. So I'm just wondering if you run some sort of experiment like that, and you know, what your opinion is with regards to, you know, this sort of optimization-based attacks that are aware of the defense mechanism.
Yeah, so that's a great question, actually, and a great point. So we've tried to do the following. We tried to say, let's assume we're the attacker. We know that the defender is taking low-rank approximation. Can I embed my attack in the low-rank factors of the data, right? So can I just push it to be in the earlier factors, right? So that's what we tried, and the attack, in some cases, the attack succeeds, but then it fails in that it distorts the data to the point that it's no longer similar to the original data, but there may be a optimization-based way of embedding that in such a way that is imperceptible that I'm not aware of. But this is a great point. We tried that, but we didn't try to fully sort of redesign all the attacks with that in mind, just but repurposing it to be in the low rank sort of regime. And so the take-home message is that it succeeds most of the time, but then it kind of fails in the human perception aspect. Like, it looks very different.
Thanks. Great.
Thank you.
So the question then is, should you still detect it as the same label if it differs?
Right.
Yeah. I have a practical question. You mentioned, you know, timing 400 seconds to do JPEG compression. Why?
Oh, this is on a batch of images.
So
yeah, this is on the entire test set. Yeah. Sorry. Yeah. Yeah, no, it doesn't take that long for, it shouldn't. No, this is on the entire test set for the benchmark, yeah.
Congratulations for the big USDA award. That's big news. And another point of contact with Kriti, actually, right? Agriculture.
Yeah, no, we have the director of citrus research here is actually from Chania, so there's a lot of points of contact.
A question to Vagelis. Hi, Vagelis.
Yes.
I wanted to ask you whether you have dealt with tensors which the set of the labels are continuous sets, like real lines and so on. Because this is a kind of very important particular class of problems, which in some case you don't have to go into very high level to meet this kind of tensors. For example, the trigonometry is full of tensors. For example, the cosine function, you remember, of course, the identity we used to learn in the high school. This means that it is a rank 2 tensor because it is a function that the cosine of x plus y, it doesn't factorize. So it needs a sum of 2 factors that multiply together. On the contrary, the exponential function is of rank 1. Okay, and what I mean by that is that essentially you can write in the form of that this is a kernel of a matrix with continuous vectors. So you can pick up a Hilbert space or a vector space of choice and pick up a continuous basis and consider these trigonometric functions as the kernels of some generalized continuous labeled matrices or even tensors. And in that case, you have, again, in front of you all the problems of factorization. And it's very nice, for example, that all these identities, they translate and they somehow reveals you what is the rank of these tensors, okay? For example, in the case when you move away from the standard cosines and sines and you go to the next non-complicated things like Bessel functions, the identities for the sum of the arguments of a Bessel function splits into a sum of infinite sum of products. So in that case, you have a very nice result, because this says that this particular, Bessel operator is of infinitely order, because you have infinitely many sums of products of the first argument times another function of the second argument. Have you ever dealt with these kind of problems?
Unfortunately not. Personally, I haven't, but it
what's your opinion? I mean,
so I would love to see a way that this could be applied to a real application where, for instance, we would like to model continuous processes like time, for example, right?
That's right, yeah.
So I would love to see that. I have not seen or done any work like that, but I would in fact love to see or even talk more about that. But I don't know more than that to have an educated answer.
Okay.
This sounds very fascinating. And
so in fact, for my forthcoming course on tensors, I just prepared a short chapter which says tensors and trigonometry. So I just expand this by taking the usual identities of trigonometric functions and translate them into a rank finding problem in this case. You don't have to do anything, simply to interpret the standard of the standard identities in terms of these tensors. So, okay, thanks.
I will talk about that in my talk on Friday. Continuous extensions of tensors for arbitrary functions of continuous variables.
Are you going to speak about trigonometry also?
No, I'm not going to talk about trigonometry, but I will talk about modeling functions of continuous variables using extensions of CPD.
Nice.
That might be of interest.
Okay. Any other question from the audience?
I have two questions, actually. Great talk, Vagelis. The first question has to do with the first part, and actually it might be a question for your student regarding rank. But because I'm not going to be here tomorrow, so I wanted to state here, like, it's not exactly a question, and it relates with algorithms. I've seen recently works by Aurora, and of course, Aurora is more like theoretical computer science, where he actually focuses on matrix factorization and how, for example, if you see matrix factorization as layers in a neural network and you keep adding layers, even if they're linear, somehow this affects and accelerates the way you train, the way you solve the problem. And I'm just thinking whether this kind of like ideas can be applied also for tensors. And I haven't like thought about this like in depth, but it's more like an idea whether like there is an implicit regularization algorithmically that instead of like, if you have a matrix and you have two factors, U and V, if you keep adding V1, V2, V3 until you get to the V, actually this somehow accelerates your performance. Of course, there's a question mark here. This is like theoretical work with some toy examples shown from Aurora, but I haven't checked it myself. And any comments on that?
That actually sounds very interesting. One thing that it reminds me of, which I mean, maybe connected in a higher level, but still, is I don't know if you know Jean Kosaifi and Yannis Panagakis from Imperial. So those folks have done a lot of work in tensorizing deep nets, in like compressing them or expressing like an entire deep net as a tensor. And I think in one of their latest work, what they do is they show that basically randomly killing away rank 1 components kind of like roughly corresponds to dropout. And so that doesn't answer your question of adding those components, but answers the connection between improving the accuracy by doing something in that component space. And so, yeah, that's the extent of my knowledge in this, but this is very interesting. I mean, this goes into the interplay of deep networks and tensor methods, right? And so I'm interested in exploring that.
Okay. And the second question is like partially answered through Dimitri's question, like whether the there is this guy Kyrillidis actually killed a lot of like attacks and defenses proposed online, but the fact that can you use somehow any information about whether like you describe something in images which is like matrices, but I'm not sure about tensors, whether you can use any information that can be very hard for the attacker to decompose. Like we know tensors come with this Like by the time you go from matrices to tensors, everything is NP hard, etc., etc. I'm not sure whether knowing this fact is going to be very difficult for an attacker like to create like an attack if you have a good defense. So any comment on that, whether like properties of tensors can be used somehow, or I have no idea, like it's a quite abstract question, I know.
That's a great point. I mean, even the fact that what we do is we stack the images, right? And that also, we do that because it also helps us understand good structure and bad structure, right? And so you could make an argument, I mean, I'm just making that argument on the fly right now, but based on what you were saying, that perhaps because of the difficulty of determining the rank there, somehow if you add maybe some randomness into play, then maybe you can obscure things. In practice, we do that. We basically randomly choose the rank for every instance, or we did different things where we added randomization in the number of components, but then we didn't really do the cat and mouse game thing. But so there may be some kind of crypto hardness constraints or hardness arguments that could be made there. That sounds really interesting. But that's the extent to what we've done there.
Okay, thank you.
Thank you.
Okay, any other questions? Okay, I think that we're approaching to the end of the first day. It was a very big pleasure to have all our former students and our former colleague here, a friend, Nikos, and all our students watching the presentations. Tomorrow is the Students' Day, so we have 3 students presenting their work. They are PhD students, and we're looking forward to it. If anybody would like to add something for today, then let's do it. Otherwise, we close for today and we renew our meeting for tomorrow at 4 o'clock.
It's very bad that we cannot not go downtown for a beer all together this time.
Yeah.
We can do it in a distributed way.
It's 9 in the morning here.
And Tasos, we can perhaps give an idea why Tasos distributing.
Tasos can join the things together.
Well, I have my subnet here, so it's your problem now. I'm doing well here, so I'm waiting for you.
You have the same subnet for all the time, okay?
Well, if I may say something, let me first thank Professor Liavas and all the TUC team for organizing this. It's a great pleasure to see all friends and former students and friends who are doing so well. But you cannot imagine how much we miss having that beer in Chania right now. All of us, we were commiserating with Yanni the other day how much we would like to be down in Chania. If it were not for this COVID thing, we would. So to be continued.
Yes. We hope so. Any other comment? Okay, thank you guys. So see some of you or those of you that can do it tomorrow at 4 o'clock. Okay? Have a nice day.
Bye-bye.
Thank you all. Thank you, folks.
Thank you, everybody.
Bye. Thank you so much.
Thank you, guys.